Did we summon 3 I/ATLAS, or was its arrival inevitable? On April 1st, 2020, astronomers using the Atlas telescope system in Hawaii confirmed that a faint greenish streak of light cutting across the sky was not bound to our Sun. Its speed, nearly 110,000 kilometers per hour, and its open hyperbolic orbit left no doubt. This was only the third confirmed interstellar object ever detected within our solar system, after Oumuamua in 2017 and 2 I/Borisov in 2019. Catalogued as 3 I/ATLAS, it carried a designation that quietly marked its place in history. The third visitor we have ever seen arrive from beyond the borders of our star system. The object's size was estimated at several hundred meters across. Unlike Oumuamua, which reflected sunlight like bare rock, 3 I/ATLAS displayed the spectral signature of typical cometary ices, but its behavior defied expectations. Astronomers calculated that it should have survived its passage near the Sun, yet before it even reached perihelion, the object disintegrated into fragments, its volatile materials dispersing into faint dust and vapor. No spacecraft could reach it in time. All we were left with was partial data, spectral traces, trajectory models, and unanswered questions. One of those questions is not purely astronomical. In the space of just 3 years, humanity went from never having seen an interstellar object to detecting 3 of them. Observational capacity has improved, but the timing raises unsettling speculation. Are these bodies simply far more common than we believed, or did human activity, our telescopes, our radio transmissions, our gravitational reach, play some role in drawing them here? That is the question that lingers over 3 I/ATLAS. What brought it into our skies, and why did it break apart before we could study it fully? The first time astronomers realized that 3 I/ATLAS was not a comet of the ordinary kind, it was not because of its brightness or its tail, but because of the numbers. When its orbital elements were first published, the eccentricity value stood out. A closed orbit within our solar system always carries an eccentricity less than 1. This object's measured eccentricity was well above that threshold, calculated at 1.11, placing it firmly on a hyperbolic path that could never loop back. That single value, rooted in the geometry of orbital mechanics, placed it among the most rare classifications, a confirmed interstellar object. No poetic interpretation was required. The math itself told us that it came from elsewhere, travelling on a trajectory that originated in the unknown depths of another system. The Atlas survey in Hawaii, short for Asteroid Terrestrial Impact Last Alert System, was built not for interstellar research but for planetary defence. Its job was to scan the skies for near-Earth objects that might one day pose a danger. Ironically, the same system built to protect Earth became the gateway for confirming a cosmic visitor. The faint smudge of 3 I/ATLAS was recorded against the shifting starfield, and as follow-up observations came in from Mauna Loa and Haleakala, then from observatories in Chile and Spain, the realization spread quickly. What we were watching was not simply another periodic comet, but something far rarer. Yet its behavior complicated the story. At first, its appearance matched what astronomers expected from a typical icy comet: an extended coma, a developing tail, and outgassing that increased as it moved toward the Sun. Spectral analysis confirmed the presence of cyanogen and carbon diatomic molecules, signatures common to cometary material, but its brightness curve was inconsistent. Predictions suggested that as it approached perihelion, roughly 0.25 astronomical units from the Sun, it would intensify into a brilliant naked eye object. Instead, it fragmented prematurely, well before reaching that distance. By mid-April 2020, telescopes reported the nucleus was no longer intact. What should have been a spectacular show became a fading cloud of debris. This premature disintegration raised new technical puzzles. Thermal models indicated that even a moderately stable comet of its estimated size should have survived the heat and gravitational stresses of its solar passage. Some speculated that its internal structure was unusually weak, perhaps a loose conglomeration of ice and dust only tenuously held together. Others pointed to the possibility of prior interactions during its interstellar journey, collisions with unseen particles or stresses from passing near another star that left it compromised long before we found it. The timing of its discovery cannot be overlooked. Oumuamua in 2017 was the first confirmed interstellar visitor, At the time, its detection seemed almost miraculous, a once-in-a-century chance observation. Then, only 2 years later, Tuohy/Borisov was spotted by an amateur astronomer in Crimea, a comet unmistakably foreign in its velocity, and in 2020, scarcely a year later, came 3I/ATLAS. In the span of just 3 years, 3 objects arrived from the galactic background into our observational reach. For a discipline where discoveries are measured in decades or centuries, this clustering appeared statistically unlikely. One explanation lies in technology. Surveys like ATLAS, Pan-STARRS, and the Zwicky Transient Facility scan wider swaths of the sky with greater sensitivity than ever before. They can detect objects as faint as 20th magnitude, something previous generations of astronomers simply could not see. From this perspective, the sudden influx of interstellar detections is not a cosmic surge but an observational revolution. They were always passing by, but only now are our instruments able to catch them. Still, there are limits to this reasoning. Oumuamua was detected because it was relatively close and reflected enough light despite lacking a bright tail. 2I/Borisov was larger and more active, making it easier to identify. 3I/ATLAS, however, was fragile, faint, and short-lived. For it to be caught at all suggests a degree of coincidence that cannot be dismissed lightly. If our surveys were marginally less sensitive, or the object slightly smaller, it would have remained unseen, lost forever in interstellar transit. This is where speculation begins. Some astronomers frame the question as one of probability. In a galaxy of hundreds of billions of stars with planetary systems ejecting debris over billions of years, interstellar wanderers must be countless. Earth just happened to build the right instruments at the right time to start noticing them. Others, however, wonder if the convergence between human readiness and cosmic arrival is itself a kind of pattern. We are building technologies not only to detect but to transmit, to send radio signals and powerful pulses into the interstellar void. Could such emissions play a role, even indirectly, in the paths these objects take? There is no mainstream evidence that human activity alters the trajectory of interstellar bodies, but the thought persists because the clustering is so unusual. In quantum physics, observation itself plays an active role, collapsing probabilities into outcomes. Extending that concept to astronomy is controversial, but the parallel is often raised. Perhaps our act of looking has consequences. Could the emergence of interstellar visitors into our detection zone be more than chance? Even within conventional science, there are other mysteries tied to 3I/ATLAS. Its point of origin remains uncertain. Backtracking its orbit suggests it came from a direction near the constellation Lynx, but tracing such a path across light years is fraught with error. Stellar motions over time distort possible origins, leaving astronomers with no definitive birthplace. Was it expelled from a binary system? Was it part of the chaotic debris left over after planetary formation around another star? The answers remain elusive, and the puzzle of its destruction lingers. If 3I/ATLAS was truly representative of cometary material formed in another star system, why did it fail so catastrophically compared to most solar comets? The gaps in our data mean that any conclusion remains tentative. What we know is that it entered, it broke apart, and it left behind only faint debris. What we do not know is whether its demise was ordinary fragility or a clue that interstellar bodies are structurally distinct from anything native to our system. But one question remains unanswered. If 3 interstellar objects could appear in such quick succession, what does that suggest about the next? The expectation after 3I/TLAS was that more interstellar objects would soon follow. If 3 had crossed our observational threshold within such a short span, statistical models suggested that many more must be moving silently through the solar system at any given moment, unobserved. Some estimates place the density of interstellar objects in the Milky Way at trillions, scattered like cosmic dust across the galactic plane. By that reasoning, the solar system should be intersected regularly by wanderers flung out from distant planetary nurseries. The difficulty lies in detection. These objects are typically small, dark, and fast-moving, making them invisible to most telescopes until they pass close enough to be briefly illuminated by the sun. For Oumuamua, visibility lasted only weeks. For 2I/Borisov, a bright coma made it accessible to both professional and amateur instruments for months. 3I/ATLAS, however, crumbled into fragments before observations could mature. This raised another issue. whether interstellar objects are more fragile than local comets. Some models propose that material formed in distant, colder systems might be less compacted, lacking the density needed to survive close solar encounters. If true, this fragility could explain why so few are detected. Many may disintegrate long before reaching observational range. The disintegration of 3I/ATLAS also posed a frustrating limit on spectroscopy. With fragments spreading and the nucleus gone, precise measurements of isotopic ratios, particularly hydrogen and oxygen, were impossible. Such ratios could have revealed whether the comet's water ice matched the isotopic signatures found in solar system bodies, or if it differed, hinting at chemical processes in a completely different star system. That missing data represents a scientific void, leaving speculation in place of certainty. And yet, there is another perspective. Some astronomers argue that the short survival of 3I/ATLAS was not merely unfortunate but potentially telling. If interstellar objects disintegrate this easily, it could mean that our solar system has been visited countless times in the past, but each visitor faded before human eyes could notice. Our modern telescopes are now fast enough and wide-field enough to catch them in their brief appearances. The coincidence may not be that we are summoning them, but that we are finally able to record their fleeting presence before they vanish. Still, the clustering remains unusual. Oumuamua in 2017, Borisov in 2019, Atlas in 2020, 3 arrivals in 3 years. Then, a pause. As of now, no confirmed fourth interstellar object has been catalogued, though candidates appear in survey data. This uneven distribution complicates the probability models. If detection were purely a function of improved technology, one would expect a steady rate of discovery, not bursts followed by silence. One explanation is observational bias. Wide-field survey programs rotate through different sky sectors at different times. An object approaching from an unsurveyed region could pass unnoticed. Another explanation is orbital mechanics. The gravitational influence of giant planets like Jupiter and Saturn may act as lenses, bending the paths of passing bodies into observable regions at certain intervals. These gravitational windows could create temporary clusters in time, concentrating detections in ways that appear unusual, but are the result of celestial dynamics rather than coincidence. Beyond these explanations lies the more speculative territory. Some researchers outside the mainstream suggest that humanity's increasing activity, our radar emissions, our deep space transmissions, our satellites beaming constant signals, acts as a beacon of sorts. In this view, interstellar objects are not actively responding, but their arrival coincides with a broader expansion of our technological footprint into space. It is less about influence and more about timing. The era in which we become capable of noticing may be the same era in which these objects naturally drift into reach. Still, the question lingers: does our act of searching create the pattern we think we see? The matter deepens when considering how improbable it is to capture an interstellar trajectory in detail. Hyperbolic orbits pass quickly, and the margin for error is thin. Even with the best instruments, tracking a faint object moving at tens of kilometers per second is difficult. Yet we caught 3 in rapid succession. Probability alone may not satisfy every observer. Could there be unseen factors shaping the frequency of arrivals? One possibility involves galactic tides. Just as the Moon influences Earth's oceans, the Milky Way's gravitational field can disturb distant reservoirs of comets surrounding other stars, occasionally ejecting them into interstellar space. If the Sun's position relative to spiral arms or stellar neighbourhoods shifts, it could encounter denser streams of such ejected bodies. In that sense, the clustering might not be human-related at all, but a reflection of our solar system passing through a busier corridor of galactic debris. Whatever the explanation, the scientific community faces a problem of readiness. Each detection so far has been reactive. We spot the object, confirm its interstellar origin, and then watch it depart or disintegrate. None has been intercepted, probed, or sampled. That leaves us dependent on brief windows of telescopic data. As more interstellar visitors appear, the challenge becomes not only to detect them, but to prepare missions that can meet them in flight. Yet this evidence raises new scientific questions. If interstellar bodies are indeed that numerous, why have we not seen them recorded in ancient astronomical texts or earlier telescopic surveys? If interstellar visitors are as common as current statistical models suggest, then a question emerges that is as much historical as it is astronomical. Why do older star catalogues, comet records, and detailed drawings from early telescopic observers not describe anything resembling a hyperbolic trajectory? Ancient civilizations were skilled skywatchers. The Babylonians kept meticulous tablets tracking planetary motions, the Chinese recorded comets and novae with precision, and medieval European astronomers routinely documented transient events in the sky. If hyperbolic visitors pass through as often in the past as they do today, should at least some record of their presence not exist? The most straightforward explanation is technological limitation. Prior to the 20th century, measuring eccentricity with enough accuracy to confirm whether an orbit was bound or unbound was extremely difficult. Observers could record the appearance of a comet, even track its changing position, but subtle deviations that indicated an escape trajectory would have been indistinguishable from highly elongated elliptical orbits. Even so, one would expect at least ambiguous references, comets that never returned, bodies that behaved irregularly. A few such records exist, but none are precise enough to be retroactively classified as interstellar. This absence raises two competing interpretations. Either interstellar visitors are rare enough that the window of human scientific maturity coincidentally aligned with their arrival, or they were passing unnoticed all along, simply too faint, too fast, or too fragile for ancient or early modern observers to detect. Both scenarios leave us unsatisfied. In one case, we confront improbable timing. In the other, we face the reality that these visitors are far more ephemeral than even our brief encounters suggest. Consider the scale of the galactic environment. Planetary systems form in dense molecular clouds, where gravitational interactions fling excess debris outward. Over billions of years, this creates a background population of wandering comets and asteroids unbound to any star. Computer simulations estimate that for every star in the galaxy, trillions of such objects may roam freely. If even a fraction of those pass near our solar system, then Earth's skies should occasionally reveal them. But occasionally in galactic terms may mean once every few decades or centuries, not annually. That makes the sudden trio of detections between 2017 and 2020 statistically remarkable, even allowing for improved technology. Some astrophysicists suggest that we are entering a new phase of observational probability, where wide-field surveys shift the baseline. Imagine trying to find meteors with the naked eye. One observer looking at a narrow patch of sky might see nothing for hours, while an all-sky camera records dozens every night. The data only appear abundant once coverage expands. In this analogy, Oumuamua and its successors are like the first meteors caught on a wide-field camera. They seem sudden, but they were always there, simply beyond reach until now. Yet there are physical dynamics that could also play a role. The gravitational environment of the solar system is not static. As the Sun moves through the galaxy, it encounters varying stellar densities, passing near other stars or dense molecular clouds every tens of millions of years. Even within shorter timescales, encounters with nearby stars can nudge interstellar debris into paths intersecting our system. For example, simulations suggest that a star known as Gliese 710 will pass within 1 light-year of the Sun in about 1.3 million years, disturbing the Oort cloud and potentially increasing comet influx. Smaller encounters, less dramatic but more frequent, may already be influencing the rate of interstellar arrivals. This perspective reframes the question. Perhaps we did not summon 3I/ATLAS. Perhaps the solar system is simply moving through a busier region of the galaxy, where ejected debris from nearby systems happens to intersect our orbit around the Milky Way. Our improved instruments then act as confirmation, catching objects we would otherwise miss. But is this coincidence of galactic movement and human readiness truly just chance, or is there something deeper to consider? Take the issue of fragility. Oumuamua did not display the classic signs of outgassing, but accelerated slightly as though pushed by some sublimation process. Its unusual shape and reflective properties remain debated. 2I/Borisov behaved more like a standard comet, with a coma and tail consistent with known physics. 3I/ATLAS began as a promising case, but broke apart prematurely, offering no chance of close study. The diversity among just 3 objects suggests that interstellar bodies are not a uniform class but a varied population, each carrying the history of its origin system. Some may be rocky fragments from disrupted planets, others icy shards from cometary belts, others still exotic mixtures that we have yet to classify. If that is the case, then every detection is a rare sample of galactic archaeology. Each visitor carries chemical signatures from a different stellar nursery. By analysing their isotopic compositions, astronomers could test theories about how common certain elements and compounds are across the galaxy. For example, if the water ice in 3I/ATLAS had survived long enough for isotopic comparison, it could have shown whether the deuterium to hydrogen ratio in its ices matched or differed from that in solar system comets. Such data would directly inform our understanding of whether Earth's oceans are unique or typical outcomes of planetary formation. The fact that the object disintegrated before this could be measured represents not only a missed opportunity, but also a scientific frustration. We know what kind of answers were just out of reach. From another angle, the clustering of discoveries may reflect nothing more than observational momentum. Once Oumuamua was found, astronomers paid closer attention to unusual orbital parameters. 2E/Borisov might otherwise have been dismissed as an eccentric comet, until its velocity and trajectory was scrutinized with interstellar expectations in mind. By the time 3I/ATLAS appeared, the community was primed to classify it quickly. In this interpretation, the so-called clustering is partly a product of heightened awareness. The visitors were not summoned, only better recognized. Still, probability remains at the center of the discussion. The chance of 3 separate interstellar objects being detected in such short order, with current estimates of interstellar density, is small but not impossible. The real test will be the coming decades. If wide-field surveys like the Vera C. Rubin Observatory in Chile, due to begin full operation soon, detect interstellar visitors every few years, then the mystery dissolves into statistics. If, however, decades pass with no new detections, the clustering of 2017 to 2020 will demand a more unusual explanation. That unusual explanation could take many forms. One is gravitational focusing, where the combined pull of the Sun and planets subtly increases the probability of interstellar debris entering observable paths at specific times. Another is temporal coincidence with galactic structures, such as density waves within the spiral arms, which may shepherd interstellar objects into certain corridors. A more speculative possibility involves resonance between planetary orbits and the timing of incoming debris streams, creating windows when detection is more likely. None of these ideas prove human involvement, but they highlight how complex the dynamics are in even a seemingly empty region of space. Yet some persist in linking human action to cosmic timing. As we expand radar astronomy, beam high-power signals into space, and launch spacecraft that alter the distribution of matter in orbit, a provocative thought emerges. Are we simply passive observers? Or are we, in ways not yet understood, participants in the larger choreography of interstellar exchange? Science offers no mechanism for our activity to attract or influence interstellar bodies, but the question persists because coincidence and pattern seeking are part of human inquiry. The clustering challenges us to consider whether the boundary between observer and participant is as firm as we assume. What cannot be denied is that 3I/ATLAS left us with fewer answers than questions. Its early breakup deprived us of detailed measurements. Its origin point remains uncertain beyond a rough direction. Its structure, fragility, and ultimate fate highlight both the promise and frustration of interstellar science. And the sequence of discoveries that brought it to our attention remains a puzzle. Was it a chance alignment of improved instruments, galactic tides, and human readiness? Or was it a sign of a deeper, less understood pattern? As one possibility fades, another emerges. If 3I/ATLAS was part of a larger stream of debris, then its siblings may already be on their way. When 3I/ATLAS first appeared in the telescopic data stream, one of the most urgent tasks was to analyse its light spectrum. By separating the faint glow of the comet into different wavelengths, astronomers could detect the chemical fingerprints of its gases and dust. This process has been a cornerstone of cometary science for over a century, allowing researchers to determine what elements and compounds are being released as solar heat drives sublimation. For 3I/ATLAS, the initial spectra revealed the presence of cyanogen and diatomic carbon. two molecules commonly observed in comets of our own solar system. At first glance, this suggested it was not an exotic outlier, but a familiar type of icy body. Yet even within this apparent normality, the details hinted at deeper mysteries. The problem is that interstellar chemistry is expected to show variations compared to the solar system standard. Planetary systems form under different conditions of temperature, density, and radiation environment. In some, the abundance of certain volatiles like carbon monoxide may be higher. In others, nitrogen compounds may dominate. By studying isotopic ratios, particularly the ratio of deuterium to hydrogen in water ice, astronomers can compare interstellar comets to local ones. This measurement is critical because it provides insight into where and how the comet formed relative to its star's disk. Unfortunately, 3I/ATLAS broke apart before its nucleus could be studied in enough detail for such precise isotopic analysis. Its disintegration scattered the material into diffuse fragments too faint for high-resolution spectroscopy, depriving us of the chance to compare its chemistry directly to that of known comets. Even so, the data that were gathered suggested that its composition was not entirely ordinary. Some reports indicated that its cyanogen emission was unusually strong compared to its overall brightness. In the solar system, comets display a wide range of cyanogen activity, but interstellar visitors might reveal even broader diversity. If 3I/ATLAS indeed had an enhanced cyanogen content, it could mean that the system it came from produced comets richer in such molecules, perhaps due to differences in the original protoplanetary nebula's chemistry. This would have been a valuable clue about the diversity of planetary formation across the galaxy had more data been available. The fact that 3I/ATLAS appeared greenish in some observations is linked to this cyanogen emission, which glows in the green portion of the spectrum under ultraviolet solar radiation. To the naked eye, had it survived, the comet might have become a striking emerald point in the night sky. Instead, by April 2020, only weeks after discovery, the object had fragmented so thoroughly that even large telescopes struggled to separate its remnants from background stars. The opportunity was lost, leaving researchers with tantalizing but incomplete information. Why did it disintegrate so suddenly? The most widely accepted explanation is structural weakness. Unlike many solar comets that have survived multiple passes near the Sun, an interstellar body like 3I/ATLAS would have been on its first such encounter. Formed billions of years ago in another system, it may have drifted in deep space at near absolute zero temperatures for eons. Its internal structure could have been extremely porous, held together only loosely by fragile ices. When exposed to the sun's heat, thermal stresses may have fractured it from within. Once cracks formed, volatile gases escaping through them would have increased the pressure, accelerating the breakup. Another possibility involves rotational instability. As comets outgaze, jets of sublimating material can act like tiny thrusters, gradually spinning the nucleus faster. If the spin rate increases beyond a critical threshold, centrifugal forces can tear the object apart. In the case of 3I/ATLAS, some models suggest that uneven outgassing might have spun it into fragmentation. This explanation, while plausible, remains speculative because direct measurements of its rotation period were never secured before it crumbled. Beyond physical explanations, the failure to preserve 3I/ATLAS has broader implications for how we study interstellar visitors. It shows that relying on ground-based telescopes alone will not be enough. If we want to understand these bodies, we need missions capable of rapid deployment, probes that can intercept and analyze them before they vanish. The European Space Agency has already proposed a mission concept called Comet Interceptor, scheduled for launch in the coming decade. While not designed exclusively for interstellar objects, it aims to station a spacecraft in a position where it can quickly redirect to intercept a newly discovered comet. Should another 3I-class visitor appear, such a mission could provide the in-situ measurements we lacked this time. But the scientific curiosity about 3I/ATLAS goes beyond chemistry and engineering. The fact that its composition seems simultaneously familiar and slightly unusual opens the door to deeper speculation. If interstellar comets share broad similarities with solar ones that suggest commonality in planetary formation across different star systems. In other words, the processes that created Earth and its neighbours are not unique. The same ices, the same organic precursors, may exist throughout the galaxy. This has profound implications for the distribution of life. If comets in other systems are chemically similar to ours, then the ingredients for biology are widespread. If, however, subtle differences emerge, like altered isotopic ratios or unexpected molecules, it could mean that planetary chemistry diverges significantly depending on the environment. The limited data from 3I/ATLAS lean towards similarity, but the evidence is too thin to settle the matter. The scientific community was particularly interested in whether 3I/ATLAS contained carbon monoxide in high abundance. In the solar system, carbon monoxide outgassing is often a marker of comets that formed in extremely cold regions of the protoplanetary disk. Some early reports suggested unusual behaviour in the gas emission rates of 3I/ATLAS, leading to speculation that it may have originated farther out from its home star than most comets we know. If that were true, it would demonstrate that interstellar space is seeded with material from the most remote and frigid zones of planetary systems, expanding our view of how far cometary bodies can form. Unfortunately, the premature breakup left too many uncertainties. No probe was in place, and ground-based telescopes had only a narrow window to collect spectra. As the fragments dispersed, sunlight scattered off dust rather than solid nucleus material, masking subtle spectral lines. By the time the comet had fully faded, astronomers were left with more questions than answers. What precise isotopic signatures did it carry? Did it contain unusual organics? Did its chemistry mirror the solar system, or did it diverge in unexpected ways? All of these remain unanswered. This gap in knowledge reinforces a broader point. Every interstellar object we detect is an opportunity not just to study a single comet, but to peer into the chemical history of another star system. These objects are messengers, fragments of alien worlds travelling for millions of years before arriving here. 3I/ATLAS was one such messenger, but its voice was lost in its premature destruction. Future missions will need to be ready to catch the next one before time runs out. The lesson is clear. Chance alone cannot be relied upon. When Oumuamua passed by, we had no probe to follow it. When Borisov arrived, we observed from afar but could not touch it. When 3I/ATLAS came, it shattered before we could learn its secrets. Each time, the limits of our preparation were exposed. The question now is whether we can adapt quickly enough to seize the next opportunity. Instruments like the Vera C. Rubin Observatory, which will scan the entire visible sky every few nights, are expected to transform discovery rates. If interstellar visitors are as common as models predict, we may soon detect dozens in a single decade. But detection is only the first step. Without rapid response missions, each one will slip through our grasp just as 3I/ATLAS did. As we consider these challenges, another layer of speculation persists. Could the clustering of these objects be more than coincidence? If human activity is not directly summoning them, could it be that our era of observational readiness coincides with a galactic cycle we do not yet fully understand? The chemistry of 3I/ATLA hints at both familiarity and difference, reminding us that our solar system is not isolated but part of a wider galactic context. What else drifts through that context, waiting for us to notice? The scientific questions are clear. How common are interstellar comets? What chemistry do they carry? How fragile are they in the face of stellar heat? But beyond those questions lies a larger one. If these objects are indeed the debris of countless other planetary systems, then each one is a fragment of a story far older and wider than our own. By failing to capture the full record of 3I/ATLAS, we lost a piece of that story. The only certainty is that more fragments are still out there, crossing the void, some destined to pass through our skies. Yet this evidence raises new scientific questions. If the chemistry of 3I/ATLAS showed both common traits and anomalies, what will the next interstellar body reveal? Will it confirm that planetary formation is universal, or will it expose differences that challenge our models of cosmic evolution? The breakup of 3I/ATLAS remains one of the most intriguing and frustrating aspects of its brief passage. In cometary science, disintegration is not unusual. Many solar system comets fragment under the combined stresses of solar heating, gravitational forces, and rotational acceleration. But what puzzled astronomers in 2020 was not that 3I/ATLAS broke apart, it was when it did. Calculations indicated that the object should have survived until at least its perihelion, the point of closest approach to the Sun. Instead, it crumbled at a distance of about 1 astronomical unit, roughly the same distance as Earth's orbit, long before reaching the far harsher conditions closer in. This early failure defied expectations, raising questions about what kind of object 3I/ATLAS really was, and whether interstellar bodies possess fundamentally different structures than comets formed within the solar system. The timeline of events was closely tracked. Discovered in late December 2019 and confirmed as interstellar on April 1st, 2020, the comet began to brighten steadily through March, fueling predictions that it might become visible to the naked eye by May. Some astronomers speculated it could even rival the brightness of Venus, an extraordinary sight for an object that had travelled across the galaxy. But those hopes collapsed abruptly when images from the Hubble Space Telescope revealed a stretched, elongated nucleus in mid-April, clear evidence of fragmentation. By late April, ground-based telescopes confirmed that the main nucleus had completely broken into multiple smaller pieces. Instead of a brilliant green comet blazing in the twilight sky, observers saw only faint diffuse clouds fading against the background of stars. Why did this happen? Several hypotheses have been proposed. The first centres on thermal stress. After travelling for millions of years in the cold of interstellar space, 3I/ATLAS would have been deeply chilled. As it approached the Sun, the rapid temperature increase could have created severe internal pressure differences. Volatile ices such as carbon monoxide or carbon dioxide, long frozen solid, may have sublimated explosively as heat penetrated the outer layers. If the comet's structure was fragile, even a modest buildup of gas could have fractured it. This explanation gains credibility from the fact that the breakup occurred earlier than expected, before the most intense solar heating, suggesting internal weakness rather than external stress as the primary cause. Another leading hypothesis involves rotational breakup. Comets are rarely perfect spheres. They are lumpy, irregular, and heterogeneous. As sunlight drives jets of gas from different regions, these jets can act like thrusters, gradually altering the rotation of the nucleus. Over time, the spin rate can increase to the point where the nucleus cannot hold itself together. For small, loosely bound bodies, this critical rotation threshold may be surprisingly low. Some researchers argue that 3I/ATLAS's nucleus, estimated at only a few hundred meters across, might have spun itself apart under the influence of outgassing jets. Unfortunately, without pre-breakup measurements of its rotation period, this hypothesis cannot be confirmed. There is also the possibility of pre-existing fractures. During its long interstellar journey, 3I/ATLAS may have experienced collisions with dust grains or small particles drifting in space. Even tiny impacts, occurring at interstellar velocities of tens of kilometers per second, could create deep fissures. These cracks, invisible to telescopes, might have left the comet structurally compromised. Once it entered the solar system, those weaknesses could have propagated quickly, leading to catastrophic failure long before the sun's heat alone would have destroyed it. In this sense, its demise may have been preordained, the final chapter of damage accumulated over eons of wandering through the galaxy. The implications of its fragility are significant. If interstellar objects are generally this unstable, then many may never survive long enough for us to observe them. They could enter the solar system, disintegrate, and disperse into dust before our surveys detect them. This would mean that the 3 interstellar visitors we have already seen, Oumuamua, Borisov, and a TLAS, represent only a fraction of the true number passing by. Most may perish unseen. That possibility both expands our understanding of how common these visitors might be and highlights the urgency of improving our detection capabilities. But the disintegration also complicates scientific interpretation. For example, brightness curves are a key tool in understanding cometary behaviour. A comet that suddenly increases in brightness may be undergoing outbursts of activity, releasing large quantities of gas and dust. For 3I/ATLAS, the brightness curve initially suggested a strong active comet that could become spectacular. After fragmentation, however, the The increased surface area of smaller fragments created a false surge in brightness, which soon collapsed as the pieces dissipated. This made it extremely difficult to model its true activity level. Some estimates of its size and mass may have been skewed by this misleading brightness behaviour. Adding to the complexity is the fact that other comets have behaved in similar, though not identical, ways. In 1999, Comet C/1999 S4, linear, also disintegrated unexpectedly before perihelion, breaking into multiple fragments and fading rapidly. More recently, in 2012, Comet SON became the subject of widespread attention, only to be destroyed during its close approach to the Sun. These precedents show that disintegration is not unique to interstellar bodies, but 3I/ATLAS's case remains notable because it occurred at a relatively safe distance, and because its interstellar nature deprived us of the chance to examine its intact nucleus. Some researchers have even considered exotic explanations. Could cosmic ray exposure over millions of years have altered the structure of 3I/ATLAS, weakening it to the point where it could not withstand solar heating? High-energy radiation can break molecular bonds and create pockets of trapped gases within ice. After countless centuries in interstellar space, such accumulated damage might create a fragile, sponge-like body prone to collapse. This idea is speculative but consistent with the notion that interstellar comets have fundamentally different histories than those native to our solar system. Beyond the technical reasons for its disintegration, the event carries broader significance. The premature death of 3I/ATLAS underscores the fleeting nature of interstellar opportunities. Unlike periodic comets that return on predictable cycles, interstellar visitors pass once and never again. Their hyperbolic trajectories carry them out of the solar system forever. When they fragment early, the chance for direct study is gone. This places enormous pressure on the astronomical community to detect and respond quickly. In 2020, no spacecraft was even remotely positioned to approach Atlas, and even if one had been, the short time frame would have made interception nearly impossible. This is why upcoming missions are so critical. Projects like Comet Interceptor are designed precisely for such contingencies, waiting in orbit until a suitable target appears. If another interstellar object is discovered, such a spacecraft could be redirected to intercept it, capturing data from a close flyby before the object disintegrates or departs. The lessons of 3I/ATLAS make clear that without such proactive readiness, we risk losing irreplaceable opportunities again and again. The disintegration also leads to an intriguing question. What if fragmentation is not a failure but a clue? Perhaps many interstellar comets are expected to break apart under solar heating, and this fragility is itself a diagnostic property. If so, then the debris of 3I/ATLAS, though faint, may still hold information. Dust particles captured in Earth's atmosphere could, in principle, contain grains shed by interstellar visitors. Identifying them is extraordinarily difficult, but some researchers are already studying micrometeorites and interplanetary dust for anomalous isotopic signatures that could betray an interstellar origin. If even a few particles from 3I/ATLAS reached Earth, they might already lie in Antarctic ice or deep-sea sediments, waiting to be discovered. There is a deeper implication still. If interstellar comets are weak, short-lived, and easily destroyed, then the vast majority of interstellar material we could study may come not from intact bodies, but from the dust and fragments they leave behind. This reframes the challenge. Rather than chasing entire comets, we may need to refine our ability to detect and analyze the fine particulate matter they shed. Space-based dust collectors, high-altitude sampling missions, and advanced spectroscopic techniques could become the tools by which we study the chemistry of other star systems indirectly through their debris. The disintegration of 3I/ATLAS was a disappointment, but it was also a lesson. It taught us that interstellar objects may not behave predictably, that their survival cannot be assumed, and that our observational windows may close without warning. It forced astronomers to confront the limits of their models and reminded us that each visitor carries not just scientific potential, but also the risk of irreversible loss. In that sense, its fragmentation is not just an end, but a challenge. Yet this evidence raises new scientific questions. If interstellar comets are so fragile that they often self-destruct before close approach, How many more pass through our solar system unseen, dissolving into dust before we can recognize them? And if fragility is their defining trait, what does that reveal about the environments that created them in the first place? The appearance of 3I/ATLAS was not only remarkable for its scientific properties, but also for the timing of its discovery. When Oumuamua was first identified in 2017, it was hailed as the first clear case of an interstellar visitor, a discovery that seemed nearly miraculous given the vastness of space and the limitations of our detection systems. Then, in 2019, 2I/Borisov was identified, and by 2020, ATLAS became the third. To go from 0 to 3 interstellar detections in the span of less than 3 years has raised a troubling statistical question. How probable is this sequence of events, and what does it suggest about the frequency of such objects? Astronomers had long suspected that interstellar debris must pass through our solar system on a regular basis. The sheer number of stars in the galaxy, each with their own planetary systems and comets, makes it almost inevitable. Dynamical models estimate that trillions of comets are ejected from young star systems during their formative years, flung into interstellar space by gravitational interactions with giant planets. Over billions of years, these orphaned bodies should saturate the galaxy. The expectation, however, was that detecting even one would be an extraordinary stroke of luck. Survey telescopes are designed to detect near-Earth asteroids, which move against the background stars in relatively predictable ways. Interstellar bodies, moving faster, and on trajectories that do not loop back toward the Sun, were thought to be far rarer in observational terms. Before Oumuamua, some models suggested we might expect to find one interstellar object every few decades at best. Others were even more pessimistic, proposing that the first discovery might not occur within the careers of working astronomers. The detection of Oumuamua immediately forced a recalibration of those expectations, suggesting that interstellar bodies were more common than thought. But when Borisov appeared just 2 years later, the statistical anomaly deepened. Was this truly the product of improved surveys, or was something unusual happening in our region of space? The case of ATLAS intensified the puzzle. To have 3 interstellar detections within a single 3-year window suggests a detection rate far higher than models predicted. If we take this at face value, then the solar system might be passing through a particularly dense stream of interstellar debris. In galactic terms, such streams are plausible. Just as comets in our solar system can form families linked to common origins, ejected interstellar debris might cluster loosely along shared paths through the galaxy. Perhaps Oumuamua, Borisov, and Atlas were not isolated wanderers but fragments of larger populations, crossing our trajectory in quick succession. However, statistical interpretation is complicated by the shifting baseline of our technology. Survey systems like Pan-STARRS, Catalina Sky Survey, and Atlas have expanded our reach dramatically in the past decade. Automated image processing, machine learning filters, and increasingly sensitive detectors have allowed astronomers to identify faint-moving objects more reliably than ever before. It is tempting to conclude that the rapid rise in interstellar detections is nothing more than a reflection of these improvements. From this perspective, the interstellar objects were always there, and only now do we have the means to see them. Yet even this explanation struggles with the numbers. The survey telescopes that found Oumuamua and Atlas were already active before 2017, scanning wide fields of sky for near-Earth objects. Why did it take so long for the first detection, and why have several arrived in such quick succession since? If the technology alone is responsible, we might expect a steadier rate of discovery rather than a sudden cluster. This uneven distribution hints at other factors influencing the frequency of encounters. One hypothesis involves galactic dynamics. The solar system orbits the center of the Milky Way roughly once every 230 million years. As it moves, it passes through different regions of varying stellar density and interstellar environment. If certain zones are richer in interstellar debris, then the solar system's position at any given time could influence the rate of encounters. We may simply be entering a part of the galaxy where interstellar material is more concentrated. This could account for the apparent uptick in detections, and if true, it means we might see even more in the coming decades. Another possibility is that large-scale gravitational interactions, perhaps involving nearby stars, have perturbed streams of interstellar material in our direction. Stellar encounters are not uncommon on astronomical timescales. A passing star can nudge comets out of its own system, creating broad flows of debris. If such a flow happens to intersect our solar system, it could result in a temporary increase in the number of visible interstellar objects. In this scenario, the trio of Oumuamua, Borisov, and Atlas may represent the leading edge of a wave of arrivals. If so, the statistical anomaly is not an anomaly at all, but the beginning of a pattern. The idea of coincidence cannot be dismissed, but even coincidence has boundaries. If random chance alone were at play, the probability of detecting 3 interstellar visitors in such a narrow time frame should be extraordinarily low. Astronomers attempting to model this sequence have struggled to reconcile it with existing theories. Either our understanding of interstellar object populations is incomplete, or our assumptions about detection efficiency are flawed. In either case, the data compel us to revise the models. There is also the human element to consider. While science rightly attributes discoveries to instruments and calculations, timing always raises subtle questions. The rapid sequence of detections coincides with an era of unprecedented observational reach. Humanity is now transmitting radio signals farther, mapping the sky with deeper surveys, and building computational frameworks that sift through vast data streams in real time. Could there be an interaction between our expanding observational footprint and the arrival of these bodies? This idea strays into speculation, but it is not wholly without precedent. In physics, the act of observation can influence outcomes at the quantum level. Extrapolating such principles to cosmic scales is controversial, but the coincidence continues to spark debate outside mainstream science. Even within strictly physical frameworks, the statistical surge invites further scrutiny. If interstellar objects are as common as the data now imply, then the galaxy may be saturated with them to a degree far beyond earlier estimates. This, in turn, has implications for planetary formation theories. It suggests that young planetary systems shed their material more violently and more frequently than previously believed. Entire reservoirs of cometary bodies could be cast adrift into interstellar space, contributing to a galactic background of wandering debris. In this light, our solar system is not unique, but merely one of countless star systems participating in a constant exchange of matter. The frequency also touches on the search for life. Interstellar comets and asteroids carry complex organic molecules, as confirmed by the analysis of Borisov. If such bodies are common, then the transport of organics between star systems, sometimes called panspermia, may be more viable than imagined. The very statistics of these detections hint at a galaxy where chemical seeds of life are continually exchanged. The sudden clustering of interstellar encounters may therefore not only be a statistical puzzle, but also a clue to the mechanisms by which life might spread across cosmic distances. Of course, one must also acknowledge the limitations of small number statistics. 3 detections, while intriguing, remain a tiny sample. Drawing sweeping conclusions from such a small dataset risks over-interpretation. It may take dozens or even hundreds of interstellar detections before clear patterns emerge. Still, the human mind is drawn to clusters and anomalies, and the rapid sequence from 2017 to 2020 remains difficult to ignore. As one possibility fades, another emerges. Perhaps the anomaly lies not in the frequency of interstellar objects, but in our expectations. If the galaxy is filled with such debris, then the true anomaly was not their sudden arrival, but our long-standing failure to detect them. The fact that it took until the 21st century to notice the first may reflect the immaturity of our observational tools rather than any rarity in the phenomena themselves. From this perspective, the statistical oddity is simply a correction, the first glimpse of a universe that has always been more dynamic and more interconnected than we realized. Yet this evidence raises new scientific questions. If interstellar bodies are indeed so abundant, how many pass through the solar system each year unseen? And more importantly, what mechanisms, gravitational, galactic or otherwise, govern the apparent clustering of their arrivals? The apparent clustering of interstellar detections cannot be examined without considering the limitations and thresholds of our detection systems. Before 2017, no confirmed interstellar visitor had ever been catalogued. Yet the solar system must have been crossed by countless such objects over billions of years. Why did we not see them earlier? The answer lies partly in how faint, fast and elusive they are, and partly in the slow progression of survey technologies that only recently became capable of noticing them. Understanding these thresholds is critical, because it reveals both the strengths and blind spots of our current observational reach. Detection begins with brightness. For a telescope to record a moving object, the object must reflect enough sunlight to stand out against the background of stars. Most interstellar bodies are likely small, tens to hundreds of meters in diameter, and covered in dark materials like carbonaceous compounds. Such surfaces reflect very little light, often less than 5% of what strikes them. Combined with their extreme distances when first entering the solar system, they remain invisible until they approach relatively close. Oumuamua, for instance, was not detected until it was already on its way out, past perihelion and receding from Earth. Even at its brightest, it was a faint point of light only observable by mid-sized telescopes. This delay illustrates the razor-thin margin of visibility that defines interstellar detection. Surveys like Pan-STARRS in Hawaii, the Catalina Sky Survey in Arizona, and ATLAS were designed primarily to find near-Earth asteroids, objects that move slowly enough across the sky to be detected by automated algorithms comparing successive images. Interstellar objects, by contrast, move much faster and on trajectories that diverge significantly from orbital patterns expected within the solar system. Their motion can confuse algorithms, producing false positives or being rejected outright as artifacts. Improvements in software have been just as important as improvements in optics. Machine learning, advanced pattern recognition, and larger data pipelines now allow faint, fast movers to be retained for further analysis instead of discarded. There is also the issue of coverage. The sky is vast, and even wide-field surveys can only cover fractions of it each night. Before the mid-2000s, much of the night sky went unmonitored at the depth required to catch faint objects. Pan-STARRS, commissioned in 2010, was the first survey capable of systematically scanning large regions with enough sensitivity to detect small, dim bodies. ATLAS, beginning operations in 2015, extended this capability, designed explicitly to catch objects on approach to Earth with only days of warning. By the time Oumuamua passed through in 2017, these systems had accumulated enough efficiency that its detection was possible, even though it had already slipped past its closest approach. The role of brightness variations adds another layer of complexity. Comets brighten as they release gas and dust when heated by the sun, but interstellar comets may behave differently. Borisov, for instance, displayed activity similar to solar system comets, making it relatively easier to detect. ATLAS also brightened as expected, until its disintegration complicated the curve. Oumuamua, however, exhibited no coma or tail, leaving only a bare, faint reflection. Had it been slightly darker or slightly smaller, it would have passed unnoticed. This demonstrates that detection thresholds are not fixed but highly dependent on the physical nature of each object. We are only seeing the subset that happens to be bright enough under our current conditions. A key turning point is on the horizon, with the Vera C. Rubin Observatory in Chile set to begin full operations in the mid-2020s. Its Legacy Survey of Space and Time, LSST, will scan the entire southern sky every few nights with unprecedented sensitivity. Objects as faint as magnitude 24 will become detectable in routine surveys, dramatically increasing the discovery rate of both asteroids and interstellar candidates. Some estimates suggest Rubin could identify several interstellar objects every year, pushing us from the era of rare anomalies into an era of statistical abundance. This will allow not just isolated case studies, but population-level analysis of interstellar debris. But even with Rubin, limitations remain. Detection depends not only on brightness, but also on geometry. If an interstellar object approaches from near the direction of the Sun, glare prevents telescopes from spotting it until too late. Oumuamua approached from a region of the sky where Pan-STARRS coverage happened to intersect its path. A different trajectory might have left it undetected. This directional bias means that our current census is incomplete and possibly skewed towards certain approach angles. Correcting for this requires not just better telescopes, but also space-based observatories positioned away from Earth's glare. Another threshold lies in time. The faster an object moves, the shorter the window for detection. Oumuamua was travelling at about 87 km per second relative to the Sun. From the moment it entered observational range to the moment it receded beyond detection, only a few weeks were available. ATLAS provided a slightly longer window, but its disintegration curtailed meaningful study. For most interstellar objects, the margin between invisibility and irretrievability is measured in months at best. This tight window underscores the need for rapid response protocols. Discoveries must be confirmed, characterized, and disseminated to the global astronomical community within days, or the opportunity is lost. These thresholds also expose a paradox. If interstellar bodies are common, then the majority remain unseen below our detection limits. Our telescopes can only probe so deep, so faint, and so fast. Just as early exoplanet searches only found hot Jupiters because those were easiest to detect, our current interstellar sample may reflect a strong observational bias. We are detecting the brightest, most conspicuous interstellar visitors, not the average. This raises caution about drawing conclusions from the limited set of 3. Future surveys may reveal a much broader diversity of interstellar objects, including darker, denser, or slower-moving varieties that elude present systems. Beyond technical challenges, there is the question of interpretation. Detection thresholds do not simply define what we see, they shape the narratives we build. The sudden appearance of 3 interstellar detections since 2017 may be less a cosmic anomaly than the natural outcome of crossing a technological tipping point. Before the mid-2000s, the threshold had not been reached. Afterward, the balance shifted. In this framing, the clustering of detections is not evidence of a galactic stream, but evidence that our eyes only just opened wide enough. The implication is profound. The sky has not changed, only our ability to notice it. And yet, even within this explanation, puzzles remain. If our thresholds are the decisive factor, why did Oumuamua, Borisov and Atlas all happen to fall within the narrow years immediately after the tipping point? Why not a gradual distribution spread evenly across the decade? The answer may involve the randomness of small numbers, but it also invites speculation about whether larger-scale cycles, gravitational alignments, galactic position, or even solar system resonances play hidden roles in shaping the arrival of interstellar bodies. There is also an uncomfortable possibility. Our thresholds are still so coarse that we may be detecting only the rare outliers, those that are unusually bright, unusually large, or unusually active. If so, the true population may be far larger than current estimates, with countless smaller or darker bodies streaming through undetected. This would suggest that interstellar debris is not a rare visitor, but a constant presence, woven invisibly into the background of the solar system. The fraction we detect is a sliver, distorted by the sharp edge of our detection limits. In this light, the role of upcoming technology cannot be overstated. The Rubin Observatory may expand our view dramatically, but space-based missions could push the threshold further still. Telescopes placed at Earth-Sun Lagrange points, or even in heliocentric orbits beyond Earth, would reduce glare and extend coverage. Infrared observatories like Neowise already hint at the potential of detecting dark bodies through their heat signatures, rather than reflected light. A dedicated infrared space survey could capture an entirely new class of interstellar visitors invisible to optical instruments. The thresholds are therefore not fixed barriers, but shifting frontiers. Each new advance redefines what counts as possible, transforming the improbable into the routine. The story of interstellar detections is not just about the objects themselves, but about the instruments that finally became capable of seeing them. It is a story of thresholds crossed and horizons widened, with each step revealing not only more of the cosmos, but also more of our own limitations. Yet this evidence raises new scientific questions. If our detection thresholds are only now allowing us to glimpse interstellar visitors, how many more have passed unnoticed, and how many more continue to slip by in the shadows just beyond our current reach? The coincidence between humanity's technological progress and the sudden appearance of interstellar detections has become a central point of discussion. For centuries, the skies were studied with the naked eye, and then through increasingly refined telescopes, yet nothing resembling 3I/ATLAS, 2I/Borisov, or Oumuamua was ever confirmed. Then, within the narrow span of just a few years, these visitors appeared in sequence, each demanding new interpretations. Is this clustering merely the result of better instruments, or does the timing reveal a deeper interaction between human observation and cosmic phenomena? This question, often phrased as human timing, has multiple layers, ranging from statistical inevitability to more speculative considerations. To understand the context, it is helpful to step back and examine the historical arc of astronomical discovery. Before the 20th century, comets were tracked by visual observers and crude photographic plates, neither of which could detect faint, fast-moving objects at great distances. Even the discovery of Pluto in 1930 required painstaking, manual comparisons of photographic plates over months. Objects on hyperbolic trajectories, moving rapidly through limited observational windows, would have been nearly impossible to identify under such conditions. The probability of missing them was effectively absolute. The post-war era brought larger ground-based observatories, but their design priorities focused on stellar and galactic astronomy, not transient solar system bodies. The true shift came in the 1990s with the advent of automated sky surveys aimed at planetary defense. Governments, concerned about the impact risk of near-Earth asteroids, funded projects like Linear, Lincoln Near-Earth Asteroid Research, which pioneered automated detection using CCD cameras and computer algorithms. Suddenly, the ability to monitor wide swaths of sky each night became routine. Tens of thousands of previously unknown asteroids were catalogued within a decade, yet still no interstellar object appeared. By the early 2000s, the sensitivity of surveys like Pan-STARRS, Catalina and Atlas increased significantly. These systems were optimized to detect faint objects moving against the background stars with high efficiency. Pan-STARRS, with its 1.8-meter telescopes and wide fields of view, became particularly effective at catching fast, faint transients. It was this system that eventually recorded the streak of Oumuamua in October 2017. Atlas, with smaller 0.5-meter telescopes but broader coverage, became complementary by monitoring more sky each night, albeit at shallower depth. This was the system that confirmed Atlas itself in 2020. The human timing question arises because these advancements were not gradual improvements, but rather step changes. Once survey technology crossed a certain threshold, the probability of detection increased dramatically. It was not that interstellar visitors suddenly began arriving, it was that we suddenly became capable of noticing them. In this sense, the clustering of Oumuamua, Borisov and Atlas can be seen as the natural outcome of reaching an observational tipping point. If our capabilities had reached this level a decade earlier, perhaps the detections would have been spread out more evenly. Yet some researchers argue that coincidence alone does not account for the tight clustering. Even at higher detection probabilities, the appearance of 3 interstellar visitors in such rapid succession seems unusual. This has led to speculation about whether external cosmic conditions also played a role. Perhaps we are passing through a region of the galaxy denser in interstellar debris, or perhaps stellar perturbations in recent millennia have nudged streams of such bodies toward our solar system. In this framing, human timing and cosmic timing overlap. We became ready to see just as a wave of interstellar material began crossing our path. Beyond these physical explanations lies a more provocative idea, that human activity itself influences detection in ways not yet fully understood. As our technological footprint expands, we alter the observational landscape of the solar system. Radio transmissions, spacecraft trajectories, and even the gravitational reach of human-launched probes extend outward. Could such activities have subtle effects on the arrival or detection of interstellar bodies? The suggestion is unconventional but worth examining. One line of speculation points to gravitational assists. Space probes launched over the past several decades have altered the orbital environment of the solar system in minor but measurable ways. Although the mass of a spacecraft is negligible compared to planets, the cumulative effect of human exploration is not zero. More plausibly, however, is that our increased monitoring makes us more likely to detect objects that would otherwise pass unnoticed. In other words, the act of observing is not changing the cosmos, but the cosmos appears to change as our observational net tightens. This is a phenomenon familiar in other sciences. What we measure expands not because the phenomena increase, but because our tools become sharper. Yet the analogy with quantum mechanics sometimes surfaces in popular discussion. At the quantum scale, observation affects the outcome of an experiment, collapsing wave functions into definite states. Could an analogous principle exist at cosmic scales, where the very act of focusing our collective observational energy on the skies correlates with the appearance of rare events? Mainstream astrophysics does not support this idea, but the coincidence of human readiness and cosmic arrival invites imaginative speculation. Whether purely metaphorical or hinting at unknown principles, The parallel between human timing and interstellar timing cannot easily be dismissed in cultural narratives. There is also the issue of global attention. The discovery of Oumuamua occurred at a time when the search for extrasolar planets had already transformed astronomy. Missions like Kepler had revealed that planets are common, and the discovery of interstellar visitors fit into a broader narrative of cosmic interconnectedness. Public interest was high, funding was available, and international collaborations were strong. In previous centuries, such a discovery might have been a curiosity noted by a handful of astronomers. In the 21st century, it became a global phenomenon almost overnight. This amplification creates the impression of clustering not just in detections but in cultural resonance. The practical consequences of human timing are significant. Because Atlas disintegrated so quickly, no spacecraft could be redirected to study it. But the very fact of its detection has accelerated mission planning. Projects like Comet Interceptor, which will wait in orbit until a suitable target appears, were conceived partly in response to the realization that interstellar visitors can appear at any time and vanish just as quickly. Human timing, in this sense, is about more than coincidence. It is about preparedness, the alignment of detection capabilities, mission readiness, and rapid response infrastructure to seize opportunities when they arise. The timing also intersects with existential questions. If interstellar debris carries complex organics, then the sudden awareness of their frequency touches directly on theories of panspermia. Perhaps life on Earth was seeded in part by such visitors. If so, then the coincidence of our readiness to detect them now carries symbolic weight. At the very moment we become capable of searching for life beyond Earth, we begin to notice the carriers of life's building blocks streaming past us. Whether coincidence or cosmic alignment, the timing seems to frame humanity's exploration of the universe within a larger arc of discovery. On the skeptical side, it is essential to remember that small number statistics can produce misleading patterns. 3 detections, while extraordinary compared to none, remain insufficient for robust conclusions. Clusters can appear by chance, and what feels like timing may simply be the randomness of early sampling. It may take dozens of detections before we can distinguish between true clustering and statistical noise. Until then, human timing may be less a cosmic mystery and more a reflection of our limited dataset. Still, the resonance of the idea persists. Our species is only now beginning to look outward with the intensity required to catch fleeting interstellar visitors. That this awareness coincides with their sudden visibility is both natural and uncanny. It reminds us that discovery is never only about the universe. It is also about the state of humanity at the moment of recognition. Our instruments, our priorities, and even our willingness to interpret anomalies shape what we see. Human timing is not an accident of chronology. It is a mirror of our readiness to engage with the cosmos. Yet this evidence raises new scientific questions. If interstellar detections align so closely with the rise of human observational power, does this mean countless others slipped past unnoticed in earlier centuries? And if so, what secrets have already passed us by, irretrievably lost to the dark? Gravitational windows describe the dynamic gateways through which interstellar bodies can enter or pass through the solar system, shaped by the gravitational influence of planets and the Sun. When an object approaches from interstellar space, its trajectory is dictated not only by its initial velocity and angle of approach, but also by how its path interacts with the gravity wells of massive bodies. The Sun exerts the dominant influence, pulling most inbound objects into hyperbolic flybys that whip them around and eject them back into interstellar space. Yet planets, particularly the gas giants, can modify these trajectories in subtle ways, sometimes slowing an object enough to alter its path through the solar system, or deflecting it into regions where detection becomes possible. Understanding these gravitational windows requires careful examination of orbital mechanics. The solar system is not a closed, static environment, but a set of overlapping gravitational fields in constant motion. Each planet creates a sphere of influence, often described by the Hill sphere, within which its gravity dominates over the Sun's. For Jupiter, this sphere extends millions of kilometers. If an interstellar object passes within this domain, its trajectory can be bent significantly, sometimes even redirected toward Earth-crossing paths. The probability of this happening depends on the relative velocities, approach angles, and timing of planetary alignments. Simulations have shown that objects passing through the outer solar system may experience multiple deflections before leaving again. For example, an interstellar fragment grazing the orbit of Neptune could be nudged closer to the Sun, where it becomes more visible to surveys. Without such gravitational assists, the object might pass at a greater distance, invisible to even the most advanced telescopes. In this sense, gravitational windows act as natural amplifiers of detection probability. They do not increase the number of interstellar visitors, but they increase the likelihood that some will stray into observational range. The case of Oumuamua illustrates this principle. Its inbound trajectory placed it on a path that crossed the inner solar system, but calculations show that it could easily have missed entirely had its approach been slightly different. Its speed of about 26 km per second relative to the Sun was too high for capture, but the exact angle allowed it to pass between the orbits of Mercury and Earth, where telescopes could detect it. This was in effect a narrow gravitational window, one that made the difference between discovery and permanent obscurity. In contrast, too, I/Borisov entered on a steeper angle, passing closer to the Sun at perihelion, and was detected while still inbound. Its brightness as an active comet helped, but again, its path was guided by the gravitational layout of the solar system. Atlas, with its trajectory and eventual fragmentation, followed a similar pattern. Each of these cases highlights how gravitational windows determine not just the movement of objects, but also our capacity to observe them. A deeper analysis reveals that planetary alignments create temporary corridors of higher probability. When Jupiter and Saturn occupy certain relative positions, their combined gravitational influence can funnel inbound debris toward the inner solar system. These alignments shift over decades and centuries, creating windows of enhanced detection potential. If humanity happened to cross into such a window, just as our surveys reached maturity, this could partly explain the clustering of recent discoveries. The universe did not change, but our vantage point through gravitational geometry did. One way to visualize this is by analogy with ocean currents. A drifting object in the sea moves not only according to its initial momentum, but also according to the flow patterns of water. Some regions funnel debris into predictable paths, while others disperse it into vast emptiness. Gravitational fields function similarly, channeling interstellar visitors into certain trajectories while excluding them from others. Earth, orbiting at 1 astronomical unit from the Sun, lies downstream of these gravitational currents. Whether we see an object depends on whether it has been funneled into our observational waters. The implications extend beyond detection. If gravitational windows can redirect interstellar bodies into orbits crossing the inner solar system, then Earth itself is periodically exposed to an elevated risk of impact. Most such objects pass harmlessly, but statistically, some fraction could intersect with Earth's orbit. The Chicxulub impactor, which ended the reign of the dinosaurs 66 million years ago, is believed to have been a comet or asteroid perturbed from the outer solar system. While not interstellar, the principle is similar. Gravitational perturbations can deliver foreign material directly to Earth. If interstellar debris follows comparable pathways, then its role in Earth's geological and biological history may be greater than currently recognized. Some researchers have suggested that gravitational focusing could even concentrate interstellar material near certain regions, such as the Sun's downwind direction relative to the galaxy. Just as the solar wind creates a heliotail, the Sun's gravity could collect passing interstellar debris into specific corridors. If this is correct, then Earth's orbit may periodically intersect with streams of material enriched in interstellar fragments. Such models remain speculative, but they highlight how gravitational geometry shapes not just individual trajectories but the larger distribution of matter entering the solar system. Another point of discussion is whether gravitational windows could allow temporary capture. Under precise conditions, an interstellar object might lose enough velocity during a planetary encounter to remain bound to the Sun for extended periods. While eventual escape is still likely, such capture could last for thousands or even millions of years. Detecting such an object would be challenging, as its orbit might resemble that of long-period comets. Some astronomers speculate that a fraction of distant objects in the Oort cloud may, in fact, be captured interstellar debris. If so, gravitational windows act not just as gateways but as filters, trapping a hidden population of interstellar bodies within our solar system. For mission planners, gravitational windows are more than theoretical curiosities. They determine whether a spacecraft can intercept an object before it escapes. The relative velocity of interstellar visitors is typically tens of kilometers per second, far faster than conventional spacecraft can match. Yet, if gravitational deflection slows or redirects a body toward the inner solar system, opportunities arise for interception. NASA and ESA studies into rapid response missions, including the proposed Comet Interceptor, rely on modelling gravitational windows to anticipate where targets might appear. Without understanding these dynamics, interception would be nearly impossible. The role of Jupiter deserves particular attention. As the largest planet, its gravitational field acts as the primary sculptor of the solar system's architecture. It protects Earth by deflecting many comets, but it also redirects material inward. In the context of interstellar visitors, Jupiter is both gatekeeper and facilitator. Some trajectories that would bypass the solar system entirely are bent inward by Jupiter's influence, increasing the chance of detection. Conversely, Jupiter can also eject objects outright, sending them back into interstellar space before we ever see them. The balance between these two roles is delicate, hinging on tiny variations in approach velocity and angle. This duality reinforces the importance of precision in modelling. A change of just a few kilometers per second, or a deflection of a fraction of a degree, can determine whether an object becomes visible to Earth-based telescopes. In this sense, gravitational windows are not fixed structures, but probabilistic corridors, their shapes shifting constantly with planetary motion. Each interstellar visitor is a test case, providing data that refine our understanding of these windows. With more detections, patterns may emerge that reveal preferred pathways into the solar system. Still, one question remains unanswered. If gravitational windows are always present, guiding streams of interstellar debris, why did humanity only begin to notice them recently? Was it merely the maturation of our observational tools, or is there a deeper synchronicity between cosmic dynamics and human awareness? The convergence of planetary alignments, observational readiness, and interstellar arrivals suggests more than coincidence. It suggests an interplay between gravitational geometry and the timing of discovery itself. Statistical anomalies form the backbone of any scientific inquiry into rare events. When astronomers detected Oumuamua in 2017, followed by Borisov in 2019, and Atlas in 2020, the sequence immediately raised eyebrows. Before these detections, no confirmed interstellar visitors had ever been catalogued in recorded history. The abrupt appearance of 3 such cases in such a narrow time span seemed improbable, almost as though nature had arranged them deliberately. To analyse this, scientists turned to probability models, asking, what are the chances of seeing so many so quickly? And does this clustering represent a genuine anomaly, or simply the product of small number statistics? The foundation of statistical reasoning lies in expectation values. Based on our current models of galactic dynamics and the density of interstellar objects, one estimate places the number of Oumuamua-sized bodies in the galaxy at roughly 10 to the 25th power. Spread across space, this density suggests that countless fragments drift between stars, many crossing the orbits of stellar systems like ours. When translated into encounter probabilities, this density implies that the solar system should experience several interstellar visitors per year, though most will remain undetected because they are faint, small, and fast. From this perspective, the anomaly is not that we suddenly found 3, it is that we had never seen any before 2017. This reframing illustrates how anomalies depend on reference points. If detection probability is low, then the long historical silence is not surprising. But as instruments became more sensitive, the expected number of detections rose sharply. Once Pan-STARRS and Atlas reached full operational capacity, the statistical expectation shifted. In that light, detecting 3 in rapid succession is consistent with revised probabilities. The anomaly lies not in the detections themselves, but in the transition period where observational limits crossed a threshold, exposing what had always been present. Yet some aspects resist easy explanation. Oumuamua's size and trajectory implied that it was not just a statistical outlier, but a representative of a vast unseen population. If one object could be detected so quickly after survey systems matured, then many more should have followed within months, not years. Borisov's appearance 2 years later, followed by Atlas a year after that, does not fully align with the expected abundance. This suggests either that our detection models overestimate the number of visible interstellar bodies, or that some clustering effect genuinely increased the local flux of visitors during this window. Clustering raises its own questions. Galactic dynamics do not distribute interstellar debris uniformly. Stars shed comets during planetary migration and gravitational interactions, creating streams that may linger for millions of years. If the solar system passed through one of these streams in recent years, then a temporary spike in detections would be expected. Such clustering would resolve the anomaly by linking it to real spatial structures rather than chance. It would also imply that the solar system is constantly traversing a cosmic landscape of debris, with detection rates rising and falling according to position within the galaxy. Another line of reasoning looks not at the objects themselves but at human biases in detection. The statistical models used to predict encounter rates assume isotropy, that objects come from all directions equally. But in practice, surveys are limited by geography, weather, and telescope design. Pan-STARRS, for example, is based in Hawaii, with its own observational constraints. Certain inbound trajectories are less likely to be scanned, creating blind spots. Thus, the true detection probability is not uniform, and anomalies may reflect these biases rather than cosmic realities. The three detections, therefore, might not be a sample of the broader population, but rather artifacts of how and where we look. Still, anomalies play a powerful role in shaping inquiry. The abrupt transition from none to three has fueled debates about whether statistical reasoning alone is sufficient. Some suggest that anomalies of this kind highlight deeper principles not yet understood. For example, if interstellar visitors arrive not randomly but in correlated groups, perhaps tied to stellar events, then our current statistical frameworks are incomplete. A nearby supernova or the disruption of a planetary system could eject multiple fragments into trajectories intersecting our solar system within decades. Detecting several in close succession would then reflect astrophysical causation rather than coincidence. The challenge is that small number statistics amplify uncertainty. With only 3 confirmed interstellar detections, every model remains provisional. A single additional detection could dramatically alter the probabilities. This uncertainty mirrors challenges in other fields, such as epidemiology or particle physics, where early results often appear anomalous until larger datasets stabilize the picture. What feels extraordinary in the moment often dissolves into normalcy once patterns are better understood. The anomaly of interstellar visitors may follow the same trajectory, appearing puzzling now, but ultimately explained by improved models. Yet anomalies also serve as catalysts. Oumuamua's detection sparked unprecedented levels of attention precisely because it was anomalous. Its unusual shape, its lack of a visible coma, and its acceleration that could not be fully explained by gravity alone magnified the sense of improbability. The anomaly was not just numerical, but physical. Borisov, by contrast, resembled a conventional comet, albeit on an interstellar path. Its conformity reinforced statistical expectations, but the pairing of such different cases in such close temporal proximity deepened the anomaly at another level. Variety within scarcity. If interstellar bodies are common, why did the first two appear so different? From a methodological standpoint, the handling of anomalies exposes the limits of statistical tools. Pure probability treats events as independent, yet astronomical processes often introduce correlations. A single stellar encounter can eject thousands of fragments, creating correlated arrivals. If we see one, the probability of seeing another rises dramatically. This undermines the assumption of independence that underpins many models. In this view, the anomaly of 3 detections is not anomalous at all. It is exactly what should be expected once a stream crosses our path. But the difficulty lies in evidence. With only 3 detections, distinguishing between random scatter and correlated clustering is impossible. Statistical anomalies at this scale do not yield clear answers. They invite speculation. And speculation is fertile ground for broader interpretations. Some frame the anomaly as evidence of panspermia, suggesting that life-bearing material arrives in bursts tied to galactic cycles. Others frame it as coincidence amplified by human readiness, the so-called anthropic anomaly. We notice only when we are capable of noticing. The anthropic angle deserves emphasis. From one perspective, anomalies are illusions born of perspective. If countless interstellar bodies have passed unnoticed for billions of years, then our sudden awareness of 3 is not cosmic strangeness but human limitation. The anomaly exists only relative to our own ignorance. In this framing, the true anomaly was the long silence, not the sudden noise. The universe was never empty, our vision was simply blind. Nevertheless, anomalies matter because they force models to evolve. They highlight mismatches between theory and observation, signalling areas where understanding is incomplete. Whether the sequence of Oumuamua, Borisov, and Atlas reflects randomness, clustering, or human bias, it compels astronomy to refine its models. Already, new surveys like the Vera Rubin Observatory's Legacy Survey of Space and Time, LSST, promise to expand the dataset exponentially. Within a decade, anomalies may give way to statistical clarity, transforming today's puzzles into tomorrow's baselines. But until then, one question persists. Are anomalies simply stepping stones on the path to understanding, or do they point to deeper patterns woven into the universe itself? Patterns that statistics alone cannot fully capture. Solar system echoes refer to the lingering effects, traces, and potential remnants of past interstellar encounters, clues that may remain long after the objects themselves have vanished into the cosmic distance. When we speak of Oumuamua, Borisov, or Atlas, we think of fleeting visitors observed within narrow windows of opportunity. But what if the solar system itself bears scars and signatures of earlier interactions? What if echoes of ancient crossings are embedded in the architecture of our planetary system, the chemistry of comets, or even the history of life on Earth? One way to examine these echoes is through the structure of the Oort cloud. This distant spherical shell of icy bodies, extending tens of thousands of astronomical units from the Sun, represents the solar system's frozen frontier. According to models, the Oort cloud formed when early planetary migrations flung countless comets outward, where they settled under the influence of galactic tides. But not all its members necessarily originated here. Some may have been captured interstellar bodies, trapped by the Sun's gravity, or by interactions with Jupiter and Saturn during the early chaotic epochs of solar system formation. If true, then the Oort cloud may function as an archive not only of our system's past, but also of debris from entirely different stellar nurseries. Evidence for such capture events remains circumstantial, but there are intriguing hints. Some long-period comets display unusual orbital inclinations, inconsistent with predictions for purely solar system-born bodies. Their eccentricities and inclinations suggest they may have entered from interstellar space and become temporarily bound. If even a fraction of the Oort cloud originated this way, then every return of a long-period comet could be a faint echo of interstellar history, a body that once belonged to another star and now cycles through ours. The Kuiper Belt, closer in, may also bear such echoes. While most Kuiper Belt objects formed in situ, computer simulations indicate that planetary migration could have exchanged debris between neighbouring systems during the Sun's early cluster environment. Stars born in the same stellar nursery as the Sun were much closer than they are today, perhaps only a fraction of a light-year apart. During that time, mutual gravitational interactions could have transferred planetesimals between systems. If so, then some fraction of today's trans-Neptunian objects may not be native but adopted. This possibility blurs the boundary between solar and interstellar material, suggesting that echoes of other stars already lie within our catalogue of solar system bodies, unrecognised as foreign because they now appear so ordinary. A different category of echoes resides not in the orbital mechanics of distant objects, but in the chemistry of comets and meteorites. Spectroscopic studies have revealed complex organic molecules in many comets, including amino acids and nucleobase precursors. Some of these molecules may have originated in the interstellar medium, where they are known to form in molecular clouds. The delivery of such material to Earth during heavy bombardment epochs could represent an echo of interstellar chemistry, embedded in the foundation of terrestrial life. If panspermia is viable, then such echoes may extend beyond molecules to biological fragments, carried across interstellar distances and seeded into young planetary environments. In this scenario, life on Earth could itself be an echo of interstellar visitors. The isotopic ratios in certain meteorites also hint at foreign origins. Anomalies in oxygen, nitrogen, and xenon isotopes suggest contributions from material predating the solar system, preserved in primitive bodies. These presolar grains are direct echoes of other stars, having condensed in the outflows of supernovae or asymptotic giant branch stars before being incorporated into the solar nebula. Their presence demonstrates that the solar system already contains interstellar echoes at the microscopic level. Each grain is a fragment of a different star's history, surviving billions of years to reach Earth. Beyond physical remnants, echoes may exist in dynamical signatures. The unusual orbit of the proposed Planet 9, for example, has been hypothesized to result from an interstellar capture event. Some models suggest that a rogue planet originally ejected from another star system may have been snared by the Sun's gravity during the early formation period. If true, such a planet would represent the largest and most dramatic echo of all, a full-sized world adopted into our family from elsewhere in the galaxy. While unconfirmed, the possibility underscores how echoes need not be subtle or microscopic. They may extend to planetary scales. More immediate echoes can also be traced through historical records of impacts. Earth's geological layers preserve evidence of catastrophic collisions with comets and asteroids. While most impactors originated in the solar system, some may have been interstellar in origin, passing through gravitational windows at just the right trajectory to collide. Distinguishing such cases is extremely difficult, but certain chemical signatures, such as isotope ratios inconsistent with solar system averages, could provide clues. If confirmed, they would extend the echoes of interstellar visitation into the deep past of Earth's biosphere, potentially linking cosmic encounters to mass extinctions or evolutionary leaps. Solar echoes may also manifest in subtle energetic effects. Oumuamua's anomalous acceleration sparked debates about non-gravitational forces. One possibility was outgassing too faint to be observed directly. But another possibility raised was that we were witnessing the echo of unfamiliar material properties, perhaps characteristic of objects formed around other stars. If future interstellar visitors display similar anomalies, then their collective behavior would constitute an echo of their origins, distinct from the comets and asteroids we know. Each detection adds to this comparative data set, allowing us to distinguish what belongs to the solar system and what carries the imprint of distant formation environments. Astronomers have even considered whether echoes might exist in the form of resonant structures. If interstellar debris repeatedly interacts with planets during crossings, it could leave behind distributions of smaller fragments or dust. Over long timescales, such residues could accumulate into faint streams, detectable through meteoroid impacts on Earth or dust signatures in space. Some sporadic meteor showers have defied clear association with known parent bodies. It is conceivable, though unproven, that a few represent the fragmented echoes of past interstellar transits, their parent bodies long gone but their debris still raining on Earth. The search for solar system echoes extends into the future as well. Missions like Comet Interceptor aim not only to study pristine comets, but also to be ready for the possibility that the target may turn out to be interstellar. If such missions capture material or map chemistry, they will provide data that distinguish solar system norms from interstellar anomalies. Each such dataset will help identify echoes already hidden within our existing catalogues. What once seemed like ordinary comets may, under new scrutiny, be revealed as emissaries from beyond. The most profound echo, however, may not be physical at all. It may be conceptual, the recognition that our solar system is not isolated, but constantly interacting with the galactic environment. Every detection of an interstellar body reminds us that boundaries are porous. Material crosses freely between stars, linking planetary systems in ways that challenge notions of separateness. From this perspective, the solar system itself is an echo of galactic processes, shaped by encounters, captures, and exchanges that bind us to the broader cosmos. And yet, one question remains. If echoes of interstellar visitors already permeate our system, embedded in comets, meteorites, and perhaps even the origins of life, how many more lie undiscovered, hidden in plain sight, waiting for us to learn how to recognize them? Resonance theories arise from the study of how repeating patterns in orbital mechanics, energy states, and cosmic interactions can synchronize disparate systems across vast distances. When astronomers speak of resonance, they often mean gravitational resonance, a condition in which two orbiting bodies exert regular, periodic gravitational influence on one another, locking their motions into predictable ratios. But in the broader context of interstellar visitors like Oumuamua, Borisov, and Atlas, resonance theories take on additional dimensions. They ask whether the clustering of detections, the peculiarities of trajectories, and the strange timing of events are not random but manifestations of deeper synchronizations at play in the cosmos. At its most basic, orbital resonance is familiar within our solar system. Jupiter's moons, Io, Europa and Ganymede, are locked into a 1 to 2 to 4 resonance, meaning that for every orbit of Ganymede, Europa completes 2 and Io completes 4. These synchronizations create tidal forces that heat Io's volcanic interior and sustain Europa's subsurface ocean. In the asteroid belt, resonances with Jupiter carve out the Kirkwood gaps, regions cleared of objects by the destabilizing tug of orbital ratios. Such structures reveal that resonance is not a marginal curiosity, but a fundamental principle shaping celestial systems. When applied to interstellar dynamics, resonance becomes more speculative but equally compelling. Some models suggest that gravitational resonances within the galaxy itself could funnel debris into streams. As stars orbit the galactic center, their gravitational fields can overlap in complex ways, especially when stellar clusters or molecular clouds interact. If resonance patterns emerge on these scales, they could periodically enhance the flow of interstellar objects through certain regions. The solar system, traversing the Milky Way at roughly 230 km per second, might therefore experience waves of heightened interstellar traffic tied to galactic resonance cycles. The clustering of Oumuamua, Borisov, and Atlas might be one such wave. Resonance theories also extend to the idea of solar planetary alignments influencing detection probabilities. While individual planetary tugs are well studied, the possibility that multiple alignments create periodic gravitational windows is still being explored. If Earth, Jupiter and Saturn align in certain configurations, their combined gravitational fields may open corridors that redirect interstellar bodies inward. This would mean that interstellar detections are not evenly distributed across time but resonate with planetary cycles. In such a framework, the timing of Oumuamua's arrival might not have been random but linked to a repeating dynamical pattern that we are only beginning to understand. Beyond gravity, resonance may manifest in energy states. In quantum physics, resonance describes how systems absorb or emit energy when frequencies match natural modes of oscillation. Some astrophysicists have speculated whether interstellar debris could carry resonance signatures from their formation environments, for instance spin states, tumbling patterns, or even the fragmentation of comets might reflect resonant interactions with parent stars or planetary systems long ago. If these resonance fingerprints persist, then each interstellar object is not just a wanderer, but a recorder of its origin environment's vibrational history. Oumuamua's unusual tumbling motion, for example, could be the echo of such a resonance, locked in during its ejection and preserved across light years. Cultural interpretations of resonance add another layer. Human civilizations have long sought patterns in celestial phenomena, interpreting alignments of planets, eclipses, and comets as signs. While modern science separates itself from astrological claims, the concept of resonance still resonates culturally because it implies interconnectedness. The discovery of 3 interstellar visitors in quick succession invites questions of cosmic rhythm, even for those steeped in rational skepticism. The very word resonance suggests harmony, cycles, and repeating motifs. To some, the clustering feels less like chance and more like a synchrony between human readiness and cosmic timing, a resonance between observer and observed. Statistically, resonance theories challenge the assumption of randomness. If interstellar objects arrive independently, then detection should follow a Poisson distribution, irregular but predictable in aggregate. Clustering, however, implies correlation. Resonance provides a mechanism for correlation without invoking improbable coincidences. Just as tidal forces synchronize moons, galactic and planetary forces might synchronize the arrival of interstellar debris. The task is to model these mechanisms rigorously and test them against observations. Until more detections are logged, resonance remains a hypothesis, but one that elegantly explains what randomness cannot. Resonance theories also intersect with panspermia. If streams of interstellar debris are shaped by galactic resonances, then the distribution of organic-rich bodies might also follow patterns. Life's building blocks could spread not uniformly but in waves, sweeping across star systems in periodic bursts. This transforms panspermia from a random scattering into a resonant process, with galactic cycles acting as the metronome. If Earth's history of impacts shows clustering consistent with such cycles, then life itself may be the product of resonance, our existence timed by cosmic rhythms older than the solar system. One fascinating application of resonance thinking lies in impact periodicity. Geological evidence suggests that mass extinctions on Earth may occur at semi-regular intervals, possibly tied to galactic oscillations. As the solar system oscillates above and below the galactic plane every tens of millions of years, gravitational tides may perturb the Oort cloud, sending showers of comets inward. If true, then resonance with the galaxy's structure dictates not only interstellar visitation, but also Earth's biological history. The interplay of celestial mechanics and terrestrial evolution would thus be bound by resonance across unimaginable scales. But resonance is not always stabilizing. It can also destabilize. The Kirkwood gaps exist because resonance with Jupiter destabilizes asteroid orbits, ejecting them into new paths. Applied to interstellar debris, resonance could act as a pump, steadily increasing the number of objects flung from their home systems. Planetary resonances around other stars may therefore be engines of ejection, contributing to the galaxy's population of wanderers. What we detect as rare anomalies may in fact be the predictable byproducts of resonant instabilities in countless distant planetary systems. The practical implications for astronomy are profound. If resonance governs the flow of interstellar debris, then detection rates will not be constant but cyclical. Planning missions to intercept such objects would therefore require forecasting these cycles, much like predicting meteor showers. The upcoming Vera Rubin Observatory, with its unparalleled survey capabilities, may be able to test resonance hypotheses by revealing whether detections cluster in time or space. If resonance is confirmed, it would transform our understanding of interstellar dynamics from random encounters to predictable patterns. Some speculative thinkers even extend resonance to the realm of consciousness. They propose that human awareness, synchronized globally by technology and communication, resonates with the cosmos in ways not yet measurable. While mainstream science does not support such claims, the metaphor persists because resonance bridges the gap between physics and perception. The clustering of interstellar detections, arriving just as humanity developed the tools to notice them, feels like resonance not just in mechanics but in meaning, a harmonic alignment between civilization and cosmos. Still, one challenge remains, distinguishing genuine resonance from the illusion of pattern. Humans are pattern-seeking creatures, prone to imposing structure where none exists. To guard against this, resonance theories must be tested with rigorous data, not just intuition. The line between meaningful correlation and random clustering is thin, and only large-scale surveys will reveal where the truth lies. Yet even as science demands caution, the allure of resonance persists. It offers a framework that unites anomalies, timing, and cosmic dynamics into a coherent whole. And yet, a question emerges from this pursuit. If resonance underlies the arrival of interstellar visitors, then what larger cycles remain unseen? Are we merely glimpsing the faint overture of a galactic symphony, with future movements yet to unfold on scales beyond our current comprehension? Telescope evolution is one of the most decisive factors in how humanity came to notice interstellar objects at all. For centuries, comets and wandering stars were described in records, often with awe but without precision. The first telescopes of the early 17th century, those of Galileo, Kepler and their contemporaries, extended vision beyond the unaided eye, but offered only a modest increase in reach. With them, observers could see the moons of Jupiter and the craters of the Moon, yet they were still blind to faint, fast-moving streaks from interstellar space. Even the largest refractors of the 19th century, which pushed glass lenses to their physical limits, were insufficient for systematic searches. These instruments could capture bright comets within the solar system, but their narrow fields of view and limited sensitivity made the sky a vast ocean with almost no nets cast across it. The transformation began with the adoption of photographic plates in the late 19th and early 20th centuries. Unlike human eyes, photographic emulsions could collect light over long exposures, making faint objects visible. Astronomers began to notice new classes of phenomena: distant galaxies, faint asteroids, and dim comets on the edge of detectability. Still, interstellar bodies were beyond reach. To detect them would require not only sensitivity, but also the ability to distinguish high-velocity trajectories from the countless slow drifts of asteroids. Without automated scanning, This task remained out of reach for observers manually comparing plates night after night. It was only in the late 20th century that technology took a decisive step forward. Charge-coupled devices, or CCDS, replaced photographic plates, offering far greater sensitivity and precision. Coupled with computer algorithms capable of scanning wide fields for motion, these digital eyes made it possible to track thousands of asteroids with unprecedented accuracy. By the early 2000s, projects like Linear, Pan-STARRS, and the Catalina Sky Survey were cataloguing near-Earth objects systematically, building the statistical frameworks that would later make anomalies stand out. What once was anecdotal became quantifiable, and in the process, the background of normalcy against which the extraordinary could be noticed was established. The Pan-STARRS telescope in Hawaii was the first to make history with Oumuamua. On October 19, 2017, it recorded a faint object moving unusually fast across the sky. At first, it was logged as a comet, but within days its trajectory was recalculated. The orbit was not elliptical, not even parabolic, but hyperbolic, with an eccentricity of about 1.2. No bound object within the solar system could display such a path. Pan-STARRS had captured the first interstellar object ever confirmed. This moment was not only a triumph of observation, but also of technological evolution, the ability to scan vast swaths of the sky with automated processing and rapid orbital determination. Without this infrastructure, Oumuamua would have passed unnoticed, just another faint streak lost among billions of stars. 2 years later, in 2019, the story repeated itself with 2I/Borisov, discovered by amateur astronomer Gennady Borisov using a custom-built telescope in Crimea. Though not as automated as Pan-STARRS, his telescope incorporated modern optics and CCD technology, combined with the persistence of manual observation. Borisov's find underscored that evolution in telescopic capability was not confined to large institutions. Advances in accessible technology allowed dedicated individuals to contribute at the very frontier of discovery. The object itself, resembling a comet with a visible coma, was easier to classify than Oumuamua, but its hyperbolic trajectory confirmed its origin beyond the solar system. By 2020, when ATLAS, Asteroid Terrestrial Impact Last Alert System, identified 3I/Atlas, telescopes were no longer just passive watchers. ATLAS was designed as an automated early warning system, capable of scanning the entire visible sky multiple times per night to detect incoming objects on collision courses with Earth. Its purpose was planetary defense, but in doing so, it provided the breadth of coverage necessary to capture anomalies like interstellar comets. The system's wide field of view and rapid cadence made it particularly adept at catching transient phenomena before they faded. 3I/ATLAS was faint, disintegrating even before perihelion, yet the data it provided was sufficient to place it in the small but growing catalogue of interstellar visitors. The significance of telescope evolution is not merely technological but conceptual. Early astronomy was observational in the sense of recording what the eye could see. Modern astronomy is computational, relying on vast data streams processed by algorithms that flag outliers. Oumuamua would not have been noticed if not for rapid orbital analysis software. ATLAS would not have distinguished its faint streak without automated detection pipelines. The shift from human-limited to machine-augmented observation is central to why interstellar objects are being discovered now, rather than in centuries past. This raises an intriguing question. Have interstellar objects always been passing through the solar system, unnoticed by earlier generations of telescopes? The answer, based on probability, is almost certainly yes. Estimates suggest that at any given time there may be thousands of interstellar objects within the orbit of Neptune, most too small or faint to detect. If that is the case, then our recent detections are not evidence of sudden cosmic change, but of technological readiness. Telescope evolution has reached the threshold where anomalies rise above the noise, and once noticed, they cannot be unseen. But some researchers speculate further. If our telescopes are evolving toward greater sensitivity, then might there be a feedback loop? The act of observation alters human awareness, and with awareness comes speculation. Interstellar detections inspire new funding, new missions, and new surveys. Each discovery accelerates the drive to find more. In this sense, telescope evolution is not just a technological arc, but a cultural resonance. humanity has entered a phase where looking outward is a priority, and the cosmos seems to answer with objects timed to our newfound vision. Whether this is coincidence or something deeper remains unsettled. Looking ahead, the next step in telescope evolution is the Vera Rubin Observatory in Chile. With its 8.4-meter mirror and the largest digital camera ever built for astronomy, 3.2 gigapixels, it will survey the entire southern sky every few nights. Its depth and cadence will dwarf all previous surveys, multiplying the chances of catching faint, fast-moving objects. Predictions suggest that once it becomes fully operational, Rubin may detect one interstellar object per year. If so, the trickle of 3 detections in 3 years will become a steady flow. This would transform the study of interstellar bodies from isolated anomalies into a systematic field. The James Webb Space Telescope also plays a role. Though not designed for wide-field surveys, its sensitivity to infrared light makes it capable of analysing the composition of interstellar visitors once they are identified. Spectroscopy at these wavelengths can reveal the molecular fingerprints of ices, organics, and dust, providing direct evidence of the chemical environments in distant star systems. In effect, telescope evolution now divides into 2 complementary branches: wide-field survey telescopes to find the visitors, and precision instruments like Webb to dissect their nature. Together, they mark the dawn of a new era where the galaxy's debris can be catalogued and studied in detail. Yet with this progress comes philosophical reflection. If telescopes are tools of perception, then their evolution parallels the expansion of human awareness itself. Each technological leap brings phenomena into existence, not because they were absent before, but because they were unseen. The interstellar objects are a perfect case study. For millennia, they passed through without notice. In just the last decade, they have entered human consciousness, altering how we think about the solar system's place in the galaxy. Telescope evolution is, in this sense, the driver of cosmic revelation. Still, questions remain. As telescopes become more powerful, what else will come into focus? Will we discover that interstellar objects are not rare anomalies but common travellers? Or will further detections reveal subtler mysteries, that their trajectories cluster, that their compositions share unusual features, that their timing correlates with patterns we do not yet understand? Each advance in telescope evolution sharpens the picture, but also deepens the puzzle. And this leads naturally to the next inquiry. If telescopes are now capable of revealing such visitors, what role does planetary defense play in shaping our interpretation of their arrival? Are these instruments, built to protect Earth from impact, also drawing us into awareness of a larger galactic traffic pattern that we had never before considered? Planetary defense is a discipline that emerged from practical necessity. For most of history, impacts from asteroids and comets were interpreted through myths or catastrophes with no scientific explanation. The Tunguska event of 1908, which flattened 2,000 square kilometers of Siberian forest, was a stark reminder that Earth is not isolated. But only in the late 20th century did planetary defense become formalized as a field where systematic surveys, orbital calculations, and contingency plans were organized under the explicit aim of protecting Earth from hazardous objects. The early motivation for planetary defense came from impact cratering studies. Lunar and planetary geology in the 1960s revealed that craters were not volcanic scars but the results of collisions. The Moon, Mars, and Mercury all bore the marks of relentless bombardment. On Earth, erosion and tectonics erased much of the evidence, but sites like Chicxulub in Mexico, tied to the extinction of the dinosaurs 66 million years ago, confirmed that impacts could reshape biological history. Once this was accepted, the question shifted from did impacts happen to when will the next one occur? That shift created the foundation of planetary defense. In 1992, the US Congress directed NASA to identify 90% of near-Earth objects larger than 1 kilometer within 10 years. These objects posed the greatest existential threat, capable of causing global climate disruption if they collided with Earth. Programs like Linear, NEAT, and later Pan-STARRS and Catalina took up the task. By the early 2000s, over 90% of these large objects had been catalogued, and none posed an imminent threat. But surveys revealed another reality. Smaller objects, in the range of 140 meters or more, remained poorly constrained. These could devastate entire regions if they struck, and their numbers ran into the tens of thousands. This expansion of scope redefined planetary defense. It was no longer about preventing global extinction, but about protecting civilization from regional catastrophes. The Chelyabinsk airburst in 2013 reinforced this urgency. A 20-meter asteroid entered Earth's atmosphere over Russia, releasing an energy equivalent to nearly 500 kilotons of TNT, shattering windows across 6 cities and injuring over 1,000 people. While small by cosmic standards, it demonstrated the vulnerability of modern infrastructure. Planetary defense shifted from a theoretical concern to a tangible, measurable necessity. Within this context, systems like ATLAS were conceived. The Asteroid Terrestrial Impact Last Alert System is not a single telescope but a network, with units in Hawaii, South Africa and Chile. Each telescope scans the sky several times per night, using wide field optics to capture rapid snapshots of any moving object. The data is processed in real time, and potential impactors can be flagged within hours of detection. The goal is not to catalogue every asteroid, but to provide days to weeks of warning if one is on a collision course. This design proved adaptable to detecting interstellar objects as well. Atlas captured 3 I/Atlas in 2020, not because it was searching specifically for interstellar bodies, but because its systematic watchfulness is sensitive to anything anomalous. Planetary defense now includes mitigation strategies as well. Detection is the first step, but what happens if an object is found on an impact trajectory? Multiple methods are under consideration. Kinetic impactors, spacecraft designed to collide with an asteroid to nudge its trajectory, were tested in 2022 with NASA's DART mission, which successfully altered the orbit of the asteroid moonlet Dimorphos. Other strategies include gravity tractors, where a spacecraft hovers near an asteroid to use its gravitational pull to shift the orbit, or nuclear devices, which could either disrupt or deflect depending on circumstances. Each of these requires early detection. The more time humanity has, the less force is needed to alter an object's path. When framed against interstellar visitors like Oumuamua, Borisov, and a TLAS, planetary defense raises deeper questions. The field is designed to protect against objects originating in the solar system, whose trajectories are calculable years or centuries in advance. Interstellar bodies complicate this picture. Their velocities are higher, often exceeding 20 to 30 kilometers per second relative to the Sun. Their paths are not influenced by long-term solar or planetary dynamics, but arrive from random directions, crossing the solar system once before vanishing forever. This means the warning times are shorter, and the feasibility of interception or mitigation is reduced. From a defense perspective, they are outliers, rare enough not to warrant dedicated protection, but intriguing enough to command scientific attention. Yet there is a conceptual overlap. Planetary defense has made humanity collectively aware of the sky not as a distant realm, but as a dynamic system with direct consequences. This awareness, in turn, creates the infrastructure for interstellar detection. Without planetary defense surveys, none of the 3 interstellar objects would have been noticed. The motivations may differ, protection versus exploration, but the outcome is the same: a sky watched closely night after night, with anomalies brought quickly into focus. The act of defense produces, almost as a byproduct, the ability to witness the extraordinary. Some thinkers have speculated whether planetary defense itself is a form of summoning, not in the literal sense of calling objects into existence, but in the sense that by creating a network of vigilance, humanity ensures that the rare becomes visible. Before telescopes scanned the sky systematically, interstellar visitors passed unseen. Once planetary defense infrastructure matured, they appeared in rapid succession. This sequence raises the unsettling but provocative idea that the act of watching transforms the landscape of what is known, giving the impression of sudden arrival where there may only have been sudden recognition. The political dimension of planetary defense also intersects with these discoveries. National space agencies, particularly NASA and ESA, have budgets allocated for detection and mitigation. But discoveries like 3I/ATLAS complicate the narrative. These are not threats in the conventional sense, but their very existence suggests that the solar system is more open to the galaxy than once believed. This has implications for security, resource planning, and even philosophical considerations of Earth's vulnerability. As planetary defense matures, it may be forced to incorporate not just solar system hazards, but the possibility of interstellar phenomena. The role of data sharing cannot be overstated. Planetary defense networks are global, with observatories and amateur astronomers contributing observations to central databases like the Minor Planet Center. This distributed vigilance ensures that objects are quickly confirmed and tracked. In the case of Oumuamua, follow-up observations were coordinated worldwide within days of discovery. For Borisov, professional and amateur astronomers alike contributed to monitoring its evolution. For Atlas, the disintegration was tracked across multiple observatories, piecing together a narrative from fragments. Planetary defense has thus created not just an infrastructure of detection, but a culture of collaboration where anomalies are global events. Critically, planetary defense highlights the tension between certainty and uncertainty. When an asteroid is discovered, orbital mechanics allows precise predictions of its path. But with interstellar objects, the timeframe for observation is narrow, and fragmentation or outgassing introduces uncertainties. The disintegration of 3I/ATLAS, for instance, left many questions unanswered, its physical structure vanishing before it could be characterized in detail. From a defensive standpoint, such uncertainties are problematic. From a scientific standpoint, they are tantalizing. Planetary defense thus finds itself at the boundary of security and discovery, where the unknown is both a hazard and an opportunity. Another layer is philosophical. Planetary defense is humanity's first coordinated attempt to manage cosmic risk. It acknowledges that Earth is not isolated, but embedded in a system where impacts are inevitable over long timescales. This shift in perspective is profound. It redefines humanity not as passive inhabitants, but as active participants in the solar system's dynamics, and when interstellar objects enter the narrative, the scale expands again, from local planetary defense to galactic context. The awareness that debris from distant star systems can cross our skies implies that defense is not just against local hazards, but against a universe in flux. Looking ahead, planetary defense may merge with interstellar science. Missions proposed to intercept fast-moving objects, like the interstellar probe concepts under discussion, could serve dual purposes, characterizing potential hazards and studying alien material. The distinction between defense and exploration may blur. Just as Atlas found 3I/Atlas, while scanning for threats, future defense systems may routinely capture interstellar visitors, turning protection into discovery. But this raises a final open question. If planetary defense infrastructure has made it possible to witness interstellar objects, are we prepared for what systematic watching will reveal? Will the catalogue of visitors grow into hundreds, showing patterns that suggest galactic rhythms? Will we find materials that point to exotic origins, challenging assumptions about planetary formation? Or will the very act of vigilance confront us with phenomena we are not yet ready to explain? Cosmic timing is the question that inevitably arises when considering the rapid sequence of interstellar discoveries. For centuries, no confirmed objects from beyond the solar system were known. Then, between 2017 and 2020, 3 such bodies, Oumuamua, Borisov and Atlas, were observed in quick succession. To some, this is a natural consequence of improved telescopes and systematic sky surveys. To others, it hints at synchronization, as though Earth's capacity to notice aligned precisely with the moment when the galaxy decided to send representatives into our neighborhood. This intersection between technological readiness and cosmic events is what gives the phrase cosmic timing its weight. The foundation of this idea begins with probabilities. Interstellar objects are expected, in theory, to pass through the solar system regularly. Astrophysical models suggest that every star ejects countless planetesimals during its formation. These fragments, unbound by gravity, drift through the galaxy indefinitely. Simulations indicate that at any given time, there should be thousands of interstellar objects within Neptune's orbit, most too small or faint to detect. By this reasoning, interstellar objects have always been here, and only now has humanity developed the means to recognize them. Cosmic timing, in this view, is less about the object's arrival, and more about human awareness catching up to an ongoing background reality. Yet the clustering of detections remains puzzling. If interstellar objects are uniformly distributed, detections should be spread across decades, not packed into a span of 3 years. One explanation is observational bias. The surveys most capable of detecting such objects only became operational in the last decade. Pan-STARRS, which spotted Oumuamua, began routine surveys in 2010. Atlas, which found 3I/ATLAS, came online in 2015. The Rubin Observatory, when it begins full operations, is expected to detect many more. Seen from this perspective, the clustering is an illusion created by a technological threshold being crossed. But the impression of sudden abundance lingers, and with it the question of timing. Timing also matters in a dynamical sense. The solar system is not stationary, but moves through the galaxy, orbiting the Milky Way's centre once every 230 million years. Along this path, it encounters regions of higher and lower stellar density, molecular clouds, and gravitational perturbations. These encounters could influence the flow of interstellar debris, creating epochs of higher influx. If the solar system is currently traversing such a region, the clustering of Oumuamua, Borisov, and Atlas might reflect not observation bias, but a genuine increase in traffic. Cosmic timing would then be astrophysical, tied to galactic structure rather than human readiness. Planetary alignments add another dimension. The gravitational fields of Jupiter, Saturn, and the other giants can bend the trajectories of passing bodies, redirecting them inward toward the inner solar system. Some simulations suggest that planetary configurations create transient funnels where the likelihood of interstellar capture or passage is enhanced. If the arrivals of Oumuamua and Atlas coincided with such alignments, then cosmic timing may be the product of orbital mechanics. The arrivals were not random but synchronized with celestial rhythms we are only beginning to map. Historical timing is also significant. The detection of interstellar objects occurred at a moment when astronomy had become globalized. Data sharing through the Minor Planet Center, rapid communication across observatories and automated processing pipelines allowed follow-up within hours. Had Oumuamua appeared a century earlier, it would have been dismissed as a faint comet and forgotten. Had Borisov appeared in the 1950s, the Cold War's fragmented scientific infrastructure might have delayed or obscured its recognition. Instead, these objects arrived in an era where anomalies are quickly noticed, debated, and preserved in memory. Cosmic timing in this sense is entangled with cultural timing. The galaxy did not change, but human society reached a stage of vigilance and coordination precisely as the visitors crossed our skies. Speculation pushes the concept further. If cosmic timing aligns detection with readiness, is there also alignment with meaning? The fact that Oumuamua appeared first, with its enigmatic elongated shape and non-gravitational acceleration, created a wave of debate about alien technology, propulsion physics, and the limits of natural explanations. Borisov followed, a more conventional comet that grounded the discussion in familiar categories. Atlas arrived next, fragmenting before it could be studied, leaving mystery but no clear resolution. The sequence almost reads like a narrative, an anomaly to spark imagination, a control case to provide comparison, and a partial object to sustain questions. Whether coincidence or not, the order amplified human engagement. Cosmic timing may be random in mechanics but resonant in perception. The statistical framework for cosmic timing remains under development. If Rubin Observatory detects 1 or 2 interstellar objects each year, the clustering of the first 3 will be reinterpreted as an artifact of small sample sizes. But if clustering persists, if detections continue to arrive in bursts rather than evenly distributed, then timing may prove to be a genuine signal. The challenge will be to distinguish patterns from noise, especially given humanity's predisposition to see order in chance. This is where the rigor of probability theory must meet the suggestiveness of coincidence. Cosmic timing also ties to broader existential questions. Earth has experienced mass extinctions, climatic shifts, and evolutionary leaps often linked to external impacts or astronomical cycles. If interstellar objects contribute to this history, then timing is not only observational, but biological. The appearance of Oumuamua and its successors might be trivial events in one era, yet in another epoch, such objects could carry materials or energies that alter the trajectory of life. Timing, in this sense, is not only about detection, but about consequence. Humanity's awareness may be arriving just as the galaxy's rhythms prepare to influence Earth once again. In philosophy of science, timing is often framed as epistemic luck, the idea that discoveries depend not only on systematic inquiry, but on being in the right place at the right time. The discovery of penicillin, the detection of cosmic microwave background radiation, the observation of pulsars, All were products of both intention and accident. Oumuamua's discovery belongs in this lineage. The telescope was scanning, but the object's trajectory brought it into view during a narrow window of detectability. Had it arrived months earlier or later, it might have escaped notice. Cosmic timing, therefore, may be nothing more than epistemic luck on a galactic scale. Yet even if coincidence explains the clustering, the effect remains transformative. The fact that humanity encountered 3 interstellar objects in such a short time has shifted perception. The solar system no longer feels closed, bounded by the sun's gravity. Instead, it is porous, open to the galaxy's wanderers. This shift in worldview is profound, regardless of whether the timing is meaningful. It repositions Earth not as an isolated system, but as a participant in galactic exchange. Looking forward, the test of cosmic timing will be accumulation. If Rubin Observatory and its successors record a steady influx, then timing will normalize, becoming routine. But if bursts of activity punctuate the record, then questions will deepen. Are these bursts tied to galactic structures, to planetary alignments, to hidden cycles we do not yet understand? The answers may take decades, requiring patient collection of data and careful disentangling of biases. One final question lingers. If cosmic timing brought Oumuamua, Borisov and Atlas into view at the dawn of systematic vigilance, what is the next stage of this alignment? Are we witnessing the opening notes of a larger pattern, where interstellar visitors become common markers of galactic rhythm? Or is this a fleeting coincidence, a brief window of anomaly before randomness reasserts itself? The uncertainty is part of the intrigue, reminding us that timing in the cosmos is measured not in years or centuries, but in cycles that stretch across millions. Throughout human history, the sudden appearance of celestial visitors has never been viewed as random. Long before astronomy provided orbital mechanics and spectroscopic data, the night sky was read as a vast text, with stars, comets, and meteors serving as omens, warnings, or messengers. The arrival of interstellar objects such as Oumuamua, Borisov, and 3/ATLAS inevitably evokes echoes of these older traditions, raising the question, are we rediscovering patterns our ancestors once understood in mythic terms? The very notion of something not of this world carries mythic weight. In ancient Mesopotamia, bright comets were called the barriers of heaven and earth, seen as intruders that crossed thresholds forbidden to mortal eyes. The Babylonians recorded their appearances on clay tablets, linking them to upheavals in kingship and shifts in fortune. Egyptian records tied unusual celestial lights to the will of Ra, manifesting as harbingers of judgment or renewal. For the Greeks, sudden stars were often interpreted as the souls of heroes ascending into eternity, or as divine portents sent by Zeus. Across cultures, the rare arrival of a new object in the sky disrupted the presumed order of the cosmos. Interstellar objects, true wanderers from beyond the solar system, fit neatly into these mythic archetypes. Unlike ordinary comets, whose returns could sometimes be predicted, these are strangers without precedent, their paths never before traced, their origins unknowable. They embody what myth consistently describes: the outsider, the messenger, the being that comes from beyond boundaries to bring revelation or chaos. The fact that their modern designations, Oumuamua meaning scout or messenger in Hawaiian, Atlas echoing the titan who carried the heavens, already bear mythic resonance reinforces the parallel. Consider the Mayan codices. In their astronomical sections, the sudden intrusion of bright objects was often linked to cycles of destruction and renewal. These were not random events, but alignments between the heavens and human destiny. In one reading, the gods communicated through such anomalies, signalling that a cosmic balance had shifted. When Oumuamua streaked past Earth in 2017, its trajectory suggested it had been travelling through interstellar space for hundreds of millions of years. To the Mayans, such an object would not have been seen as a mere rock, but as a messenger deliberately timed to intersect with humanity's age. In Norse mythology, the heavens are fragile, threaded together by Yggdrasil, the world tree. Unusual lights in the sky were thought to be sparks from its branches or omens of Ragnarok, the end of cycles. When 3/ATLAS fragmented before reaching perihelion, the image recalls myths of divine weapons shattering before their task is complete, or omens that appear briefly and vanish, leaving mortals uncertain of their meaning. The Norse sagas warn that such signs are never to be dismissed. They are the preludes to transformations yet unseen. The pattern becomes even clearer when looking at cultures that saw comets as hairy stars. The Chinese, meticulous skywatchers for millennia, compiled detailed records of cometary appearances. They interpreted them as guest stars, intruding into constellations like uninvited visitors. The very term resonates with Oumuamua, Borisov, and Atlas, which are literally galactic guests in the solar system. Chinese chronicles sometimes link these stars to dynastic change or calamity, not out of superstition, but from a recognition that the cosmos and human affairs were woven into the same fabric. The arrival of interstellar objects today invites a similar reflection. Are we projecting meaning onto randomness, or are we glimpsing deeper synchrony? There is also the archetype of the green comet 3I/ATLAS, observed before its disintegration, had a greenish hue, caused by diatomic carbon fluorescing under solar radiation. In folklore, green comets were often linked to pestilence or purification. In medieval Europe, the sudden appearance of green-tinged comets coincided with outbreaks of plague, reinforcing their association with death and transformation. While modern science understands the chemistry, the mythic weight persists. Atlas's green shimmer evokes not just a chemical reaction, but an ancestral memory of danger wrapped in beauty. Another striking parallel lies in the shattering of ATLAS. In myth, visitors from beyond rarely depart intact. They leave fragments, artifacts, symbols, or legacies that endure long after their physical presence is gone. In Greek tales, Prometheus descends from the heavens, bringing fire, but is broken and bound for his trespass. In Polynesian tradition, celestial messengers often disintegrated, their remains becoming sacred stones or islands. In a sense, ATLAS followed the same arc, arriving whole, breaking apart, leaving humanity only with fragments of data and lingering questions. The narrative is mythic even in scientific terms. The question then arises, why do these parallels matter? One possibility is that mythology encoded a recognition of patterns long before science. Interstellar visitors may be rare, but their impact on human imagination is disproportionate. When one appears, it disrupts certainty. It forces societies to ask what lies beyond the visible horizon. Myth responded with stories of gods and portents. Science responds with models and probabilities. But the underlying sense of intrusion, of boundary crossing, remains the same. Psychologically, these objects embody what Jung would call archetypes, universal symbols arising from the collective unconscious. The stranger, the messenger, the herald of change, all recur across cultures because they reflect fundamental aspects of human experience. Interstellar objects, in their sudden and mysterious arrivals, trigger these archetypes on a cosmic scale. Oumuamua's elongated shape, so unlike ordinary comets, immediately sparked speculation of alien probes. Atlas's disintegration evoked the myth of fleeting omens. Even Borisov, more conventional in appearance, reinforced the archetype of the traveller, who confirms that others exist beyond known boundaries. There is also a modern mythos forming around these events. Popular media framed Oumuamua as a potential alien artifact, echoing Arthur C. Clarke's Rendezvous with Rama. Atlas, though less publicised, was still described in headlines as the comet that came from another star. The very language is myth-making, turning raw data into story. Humanity cannot help but narrativize, to see in these objects not only icy fragments, but symbols of connection to a larger cosmos. Mythic parallels also caution us. In many traditions, ignoring or dismissing celestial signs brought ruin. The Roman historian Cassius Dio recorded that before the assassination of Julius Caesar, a comet blazed across the sky. The Aztecs believed comets foretold the arrival of strangers and upheaval of empires, a belief vindicated tragically by the coming of the Spanish. If today we encounter interstellar objects and reduce them only to data points, are we missing their symbolic warning? Perhaps the mythic lens suggests that such visitors mark thresholds, moments when humanity must prepare for transition, whether technological, ecological, or even existential. The resonance deepens when considering that modern humanity, unlike ancient societies, has the ability to respond. We can model trajectories, plan missions, even dream of interceptors that might one day chase such visitors. But myth reminds us that power does not erase meaning. To see Atlas fragment is to experience the same awe and uncertainty our ancestors felt when comets blazed and vanished. The mythic parallel is not a quaint echo of the past, it is a recognition that our psychological relationship to the cosmos remains unchanged. Ultimately, the parallels between interstellar visitors and mythic messengers serve as a bridge. They remind us that science and myth are not opposed but complementary modes of engaging with mystery. Science asks how these objects move, what they are made of, how often they arrive. Myth asks why they come now, what they signify, what role they play in the human story. Together they frame the enigma of 3I/ATLAS, not only as a fragmenting comet, but as part of a pattern stretching from clay tablets in Mesopotamia to telescopes in Hawaii. Perhaps the deepest parallel is the sense of being addressed. Myth teaches that when the heavens send signs, they are not impersonal, they are invitations to pay attention. Interstellar objects, by their rarity, may be just that, a galactic reminder that humanity is not isolated, that the universe is larger, stranger, and more interconnected than we imagined. Whether we interpret that reminder as omen, opportunity, or coincidence is our choice. But to see Atlas dissolve in the light of the sun, and feel wonder, unease, and curiosity all at once, that is the mythic experience itself, alive in the modern age. For all the mythic parallels that human culture has attached to celestial intruders, science now offers a lens that can quantify just how unusual these events really are. Numbers strip away superstition, but they replace it with a different kind of awe. To see an interstellar object like Oumuamua, Borisov, or 3I/ATLAS is not just rare in human history, it is statistically extraordinary in the context of the solar system's scale and the galaxy's population. Understanding how improbable such encounters are requires unpacking both observation bias and astrophysical probability. Until 2017, no confirmed interstellar objects had ever been observed. Telescopes surveyed the sky for decades, cataloguing hundreds of thousands of asteroids and comets, but every single one was gravitationally bound to the Sun. When Oumuamua was first detected on October 19, 2017, by the Pan-STARRS 1 telescope in Hawaii, its velocity relative to the Sun immediately set it apart. At about 87 kilometers per second, it was moving too fast to have originated within the solar system. That single detection rewrote expectations overnight. If we had been observing the sky for so long and never seen such an object, but then one appeared suddenly, what did that imply about their true population? Astronomers quickly turned to statistical modelling. The logic was simple. If telescopes only catch a fraction of the objects that pass near Earth, then seeing even one implies a hidden swarm of countless others. Based on Oumuamua's detection parameters, Harvard astronomers estimated that for every cubic parsec of space in the galaxy, there may be about 1 quadrillion interstellar objects of similar size. To put this into perspective, that would mean our Milky Way alone contains roughly as many interstellar wanderers as there are stars. The solar system, then, is not an isolated bubble, but a zone constantly brushed by debris from other suns. But the rarity lies not in their existence, it lies in our ability to detect them. The sky is vast, detection windows are narrow, and only in the last decade have survey telescopes gained the sensitivity to spot such fast-moving dim visitors. Oumuamua was already receding when it was discovered, meaning we caught only a fleeting glimpse. If its path had been slightly different, or if it had entered just a few months earlier, Earth would never have known it passed. The odds of detection were razor thin, underscoring how many others must have gone unnoticed. Then came Borisov in August 2019, a comet with a coma and tail clearly visible, and its hyperbolic orbit confirmed its interstellar origin. Unlike Oumuamua, Borisov resembled a typical comet in shape and behaviour. Its presence validated the idea that interstellar objects are not anomalies, but part of a continuous galactic traffic. Statistically, the chance of detecting 2 such objects in just 2 years after centuries of silence seemed almost implausible. Either humanity had entered an observational golden age, or the density of these wanderers was far greater than earlier models predicted. The arrival of 3I/ATLAS in 2020 compounded the puzzle. Though it fragmented before reaching its closest approach, its trajectory matched the interstellar profile. In 3 years, we had 3 interstellar detections. By statistical reasoning, this was either an incredible coincidence or an indicator that the population of such bodies is immense. But here is where rarity becomes paradoxical. On the one hand, interstellar objects may number in the quadrillions across the galaxy. On the other hand, the chance of any given one crossing close enough to Earth to be detected is still vanishingly small. To illustrate, imagine standing on a beach, watching the ocean. Countless grains of sand exist, but only a few will be swept by waves to land directly at your feet. The solar system is that shoreline. It is constantly exposed to the galactic tide, but only rarely does debris drift close enough for us to notice. Astrophysicists have modelled expected detection rates with upcoming instruments. The Vera C. Rubin Observatory in Chile, expected to begin its legacy survey of space and time, LSST, within the decade, will scan the entire visible sky every few nights. With its unprecedented sensitivity, Rubin is predicted to detect at least 1 interstellar object every year, perhaps more. That statistic reveals something profound. What seemed mythically rare in the past may soon become routine, not because the events are more common, but because our instruments have finally reached the threshold to perceive them. This leads to a curious reflection. Statistically, interstellar objects may have always swept through the solar system, perhaps every few months or years. Humanity simply lacked the means to see them. Their rarity was not in reality, but in perception. Ancient myths, then, may have been based on only a handful of visible anomalies over centuries, amplifying their symbolic power. Modern science, with improved tools, can normalize them, but at the cost of stripping away some of their rarity. Or perhaps, as myth suggests, the timing of their discovery now is itself meaningful. The question of probability extends further when considering the odds of encountering objects large enough to matter on planetary scales. Models suggest that over the lifetime of the Earth, dozens to hundreds of interstellar comets may have collided with our planet. If true, then the statistical rarity of observing them today contrasts with their potentially frequent role in geological history. Could an interstellar impact have contributed to mass extinctions or to the delivery of exotic organic molecules that seeded life? Probability calculations cannot yet confirm such specific events, but the odds are not negligible. Another statistical layer concerns the shapes and behaviours of these objects. Oumuamua's elongated, possibly pancake-like profile, combined with its anomalous acceleration, made it statistically unusual compared to known comets and asteroids. Borisov's similarity to solar comets made it less strange. Atlas, fragmenting before observation could fully probe it, left an incomplete dataset. If, over time, we detect many more interstellar objects, we can build a statistical profile of their properties. Do most resemble Borisov, or do many defy expectations like Oumuamua? The rarity of their shapes may itself point to diverse formation environments across the galaxy. Rarity also touches on the philosophical. When only 3 interstellar objects are known, each becomes disproportionately important, serving as the anchor for sweeping inferences. Yet 3 data points in science are statistically fragile. Extrapolations to a quadrillion unseen objects rest on delicate assumptions. This scarcity makes every new detection not just another discovery, but a crucial piece in a puzzle where each piece radically shifts the picture. In statistics, small samples carry wide margins of error, but they also hold immense potential to redefine probabilities when expanded. Finally, we must consider human rarity. Statistically, the probability that a technological species arises, develops telescopes, and happens to exist at the moment when survey capabilities align with interstellar visitor arrivals is itself extraordinary. In billions of years of Earth's history, the overlap between interstellar crossings and human scientific awareness may represent only the briefest sliver. From this perspective, the rarity is not only in the objects, but in us, a species able to notice, measure, and wonder about them at all. Thus, the statistical rarity of interstellar objects can be summarized as layered paradox. They are common in the galaxy but rarely visible. They may have crossed our skies countless times, but only now enter our scientific record. They are numerically vast yet individually precious, and their appearance at this exact stage of human development may be the rarest alignment of all. But as probabilities are refined, one question emerges. If these visitors are far more common than once believed, how long before we encounter one that refuses to fit any category? One whose rarity cannot be explained by numbers alone? Velocity defines identity in astronomy. The speed and trajectory of an object reveal whether it belongs to the Sun's family or whether it is a wanderer from elsewhere. Interstellar objects stand out because their velocities exceed the limits of gravitational binding. Yet within this category, some exhibit motion so unusual that they strain even interstellar expectations. The story of anomalous velocities begins with Oumuamua, but extends to every interstellar detection since, raising questions about what forces propel these travellers and whether some may represent mechanisms unknown to conventional astrophysics. When Oumuamua was first observed in October 2017, its heliocentric velocity was measured at approximately 26 km per second before perihelion, increasing to 87 km per second relative to the Sun as it swung past. This alone marked it as interstellar. But as data accumulated, astronomers noticed something peculiar. After its closest approach, Oumuamua was receding faster than expected. Its trajectory deviated slightly from the path predicted by pure gravity. The acceleration was small, on the order of 0.00083 meters per second squared, but it was statistically significant, detectable over the weeks of tracking. The most straightforward explanation was outgassing, the standard cometry process where sublimating ices jet material away, producing thrust. Yet no coma, tail, or gas emissions were detected despite sensitive searches. In fact, Oumuamua appeared entirely inert, with a brightness curve consistent with a rocky body or perhaps a surface covered in organic crust. If outgassing occurred, it must have been extraordinarily subtle, invisible even to the Hubble Space Telescope. The velocity anomaly, therefore, sparked speculation. Harvard astronomer Avi Loeb suggested an alternative, that Oumuamua might be a thin, flat structure propelled by solar radiation pressure. In this model, sunlight itself provided the acceleration, as if the object were a natural or artificial solar sail. The idea divided the astronomical community. Many argued that exotic explanations were unnecessary, that novel forms of outgassing or unusual shapes could suffice. But the anomaly remained unexplained within standard categories. Here, velocity was not merely a measurement, but a clue pointing beyond known mechanisms. Borisov, the second confirmed interstellar object, offered a useful comparison. Its incoming velocity relative to the Sun was about 32 km per second, consistent with galactic orbital speeds. More importantly, its trajectory followed gravitational predictions precisely, with no anomalous accelerations detected. Unlike Oumuamua, Borisov displayed an active coma, a tail, and the familiar behaviour of a comet. Its velocity, while interstellar, was not anomalous in the same sense. This contrast sharpened the mystery. Why would one interstellar object deviate and another conform? Was Oumuamua unique, or simply the first hint of a class of anomalous movers? Then came 3 I/ATLAS. Its initial trajectory suggested an interstellar origin, with an incoming velocity consistent with escape from another star system. But before perihelion, ATLAS fragmented, leaving astronomers with incomplete velocity data. Some fragments continued on hyperbolic paths, others dispersed into trails too faint to track. The breakup prevented precise analysis of whether ATLAS exhibited subtle non-gravitational accelerations like Oumuamua. Its disintegration echoed the fate of some solar comets, yet the opportunity to measure another anomalous velocity was lost. What makes velocity anomalies so significant is their diagnostic power. In celestial mechanics, gravity alone produces clean, predictable curves. Any deviation implies additional forces at play. In the solar system, we understand these forces: outgassing, radiation pressure, tidal effects, or relativistic corrections. For interstellar objects, however, velocities may encode conditions from entirely different formation environments. Anomalies are not noise, they are potential signatures of unfamiliar physics or exotic processes. Consider the range of possibilities. If Oumuamua's acceleration was due to radiation pressure, its structure must have been unusually thin, on the order of millimeters thick and tens of meters across. Such geometries are not known in natural solar system bodies, which tend toward more compact shapes. If future interstellar visitors exhibit similar accelerations, then a new class of ultra-thin, high area-to-mass ratio bodies may need to be recognized. Their formation mechanisms remain unknown, perhaps fragments of disrupted planets, ejected sheets of ices, or other exotic origins. Alternatively, if outgassing was responsible, then the lack of visible emissions suggests unusual chemistry. Some have proposed hydrogen ice, sublimating invisibly, or carbon monoxide outflows too faint to detect. Yet hydrogen ice is unlikely to survive interstellar journeys without erosion, and the required volumes strain plausibility. Velocity anomalies, in this sense, challenge not only observation but theory itself. From a galactic perspective, velocities also matter because they trace origins. The solar system orbits the galactic center at about 220 kilometers per second. Nearby stars share similar velocities, with relative motions typically in the tens of kilometers per second range. Oumuamua's incoming vector aligned roughly with the local standard of rest, the average motion of stars in the Sun's neighborhood. Statistically, this is surprising. Random interstellar bodies should reflect the varied velocities of their parent stars. For Oumuamua to arrive so close to the local standard of rest suggests either coincidence or some dynamical filtering process. Was it slowed relative to its birth system, or is there a population of interstellar debris orbiting the galaxy in near synchrony with local stars? Its anomalous velocity was not just in acceleration but in its baseline alignment. Borisov, by contrast, had an incoming trajectory more typical of stellar scatter, less aligned with the local standard of rest. Atlas's trajectory was too incomplete to settle into either pattern. Statistically then, with only 3 examples, we already see diversity. This raises the possibility of multiple populations, ordinary interstellar comets like Borisov, anomalous accelerators like Oumuamua, and fragmenting bodies like Aetalus. If so, velocity anomalies may become the key to distinguishing categories. Future detection capabilities promise to clarify. The Vera C. Rubin Observatory will not only increase the rate of interstellar object discoveries, but also provide more precise velocity measurements over longer arcs. If anomalies like Oumuamua's recur, the statistical case will strengthen. If not, then its singular deviation will appear even more remarkable, perhaps marking it as an outlier of unknown origin. In either outcome, velocities will define the taxonomy of interstellar objects as much as composition or shape. Philosophically, anomalous velocities carry implications that extend beyond astrophysics. They force us to consider whether we are encountering phenomena outside our current categories. In the history of science, anomalies often herald paradigm shifts. The orbit of Mercury, deviating from Newtonian predictions, led to general relativity. The ultraviolet catastrophe and blackbody radiation gave birth to quantum mechanics. Could the anomalous velocity of Oumuamua play a similar role, pointing toward gaps in our understanding of interstellar material dynamics? Equally, anomalous velocities fuel speculation. The possibility of artificial origin, though controversial, arises precisely because velocity is measurable and resistant to reinterpretation. An object moving in a way gravity cannot explain invites questions of propulsion, design, and intent. While most astronomers resist such conclusions without stronger evidence, the anomaly itself remains undeniable. It is a reminder that science advances not by dismissing anomalies, but by investigating them until they are either absorbed into existing frameworks or demand new ones. Thus, anomalous velocities sit at the crossroads of observation and theory, grounding speculation in hard data while resisting easy classification. Oumuamua's acceleration may one day be explained by chemistry or geometry, but until multiple similar cases are observed, its deviation stands as a singular puzzle. Borisov confirms that not all interstellar visitors are anomalous. Atlas leaves only questions, and the next detection may either normalize the pattern or deepen the mystery. But even if anomalies become common, one question persists. If some interstellar bodies move in ways that defy natural explanation, are we prepared to recognize the possibility that their velocities may not be accidents of physics, but signatures of intent? Not every interstellar visitor is destined to leave. Though Oumuamua, Borisov, and 3I/ATLAS all crossed the solar system on hyperbolic paths, their encounters revive a long-standing question in celestial mechanics. Could some interstellar bodies be captured permanently or temporarily by the Sun's gravity? If so, then the solar system may already contain alien debris hidden among its countless comets and asteroids, relics of stellar neighborhoods long since dissolved. The mathematics of capture are not simple. A body entering the solar system from interstellar space arrives with a high velocity relative to the Sun. For it to remain bound, that velocity must be dissipated or redirected so that the object loses enough energy to fall into a closed orbit. Gravity alone cannot achieve this. In a two-body interaction, the object will always swing past and escape. But add a third body, a planet for instance, and the possibilities change. A gravitational assist can transfer momentum between bodies, slowing one while speeding another. This is how spacecraft use planetary flybys to reach the outer solar system. In principle, an interstellar comet could undergo the same exchange, losing enough velocity to become trapped. Jupiter, with its enormous mass, is the primary candidate for such captures. Simulations suggest that Jupiter family comets, those with short orbital periods, may include some that originated not in the solar nebula but as interstellar wanderers that happen to pass close enough to be redirected. The probability is low because the geometry must be exact. But over billions of years, even rare events accumulate. Estimates suggest that at any given time, there could be a handful of captured interstellar comets residing undetected in the solar system, their orbits indistinguishable from native bodies unless their chemistry betrays them. Another possibility is temporary capture. In this case, an object may loop around the Sun or a planet for a few orbits before escaping again. Such events have been observed with solar system comets. For an interstellar body, temporary capture could extend its residence from a brief flyby of months to a stay of decades or centuries. During that time, it could undergo outgassing, fragmentation, or collisions, leaving material behind. The debris of such encounters might persist even after the original body departs, embedding interstellar signatures in the dust streams or meteor showers of Earth. Intriguingly, some researchers have proposed that certain long-period comets with unusual orbits could be captured interstellar objects. Their inclinations and eccentricities do not fit neatly within models of solar system formation. If isotopic analysis of their material one day shows ratios incompatible with solar norms, capture will move from hypothesis to confirmation. Already, meteorites on Earth contain pre-solar grains, microscopic inclusions from other stars. These are known to have been inherited from the interstellar medium during the Sun's birth. But a larger captured body would represent an intact macroscopic artifact, a time capsule of conditions around a different star system. Capture hypotheses also extend to the speculative notion of rogue planets. These are planets ejected from their birth systems, drifting freely through the galaxy. Simulations suggest billions may exist, wandering dark between the stars. If one passed near the Sun in the early epochs, when the solar system was still embedded in its dense stellar nursery, capture might have been possible. Some theories of the hypothetical Planet 9, a large distant world whose gravitational influence is inferred from clustering of trans-Neptunian objects, suggest it could be such a captured rogue. If true, then the solar system already hosts not just interstellar comets, but an interstellar planet. The mechanics of capture depend heavily on timing. During the Sun's first 100 million years, it resided within a stellar cluster where encounters with other stars were frequent. Relative velocities were lower, and gravitational interactions more common. This was the optimal period for interstellar capture. Today, in the Sun's more isolated galactic orbit, chances are far slimmer. Yet even in the present epoch, occasional captures are not impossible. The discovery of centaurs, small bodies orbiting between Jupiter and Neptune, includes examples with properties that may hint at interstellar origin. Distinguishing them requires deep chemical sampling, which current technology rarely provides. There is also the possibility of partial capture. An object may pass through the solar system, leaving fragments that remain bound. The disintegration of ATLAS illustrates the principle. While the core continued outward on a hyperbolic trajectory, some debris may have been slowed sufficiently by solar radiation and gravitational interactions to remain within the solar system. Over time, these fragments would disperse, blending into the population of faint dust and meteoroids. Tracing them back to an interstellar origin would be challenging, but not impossible. Laboratory analysis of micrometeorites collected in Earth's stratosphere has already revealed isotopic anomalies consistent with pre-solar sources. From a statistical standpoint, capture is a low probability process, but given the vast timescales involved, even rare probabilities become inevitabilities. The solar system is 4.6 billion years old. If quadrillions of interstellar objects wander the galaxy, then over that span millions must have crossed the Sun's gravitational sphere of influence. Even if only a fraction of a percent were captured, the cumulative number could be significant. The difficulty is recognition. Captured interstellar bodies would appear outwardly similar to native ones, requiring careful isotopic or spectroscopic distinction. Until such measurements are routine, the hypothesis remains largely theoretical, yet the implications are profound. If interstellar bodies have been captured, then the solar system is not a closed system, but a mosaic of material from many stellar sources. Each capture would add to the diversity of building blocks available for planets, moons, and life. Some of Earth's water, delivered by comets, could in principle trace back to alien stars. Organic compounds deposited by captured bodies could have contributed to prebiotic chemistry. Even life, if panspermia operates, could have hitchhiked across such captured messengers. Capture, therefore, is not merely a dynamical curiosity. It is a mechanism of cosmic exchange. There is also a cautionary angle. A large captured body could eventually destabilize existing orbits. If Planet 9 exists and is interstellar in origin, its capture altered the architecture of the outer solar system, shaping the orbits of countless small bodies. Similarly, a captured comet on a long-period orbit could one day intersect Earth's path. Statistically rare, but not impossible. Thus, capture is not only a window into the past, but also a factor in assessing planetary defense. Looking forward, missions designed to rendezvous with interstellar objects may provide decisive tests. If one is detected early enough, spacecraft could intercept it, sampling material directly. A chemical profile inconsistent with solar system formation would be unambiguous evidence of foreign origin. Should we one day find an object already bound to the solar system but chemically alien, capture will no longer be hypothesis but reality. Until then, the question lingers. Are we surrounded only by native comets and asteroids, or do a few silent interstellar captives already circle the Sun, indistinguishable from locals? And if they are here, how many secrets of other worlds lie hidden in their cores, waiting to be uncovered? The discovery of 3I/ATLAS inevitably reignited discussions that began with Oumuamua. When the Pan-STARRS telescope first detected that elongated object in October 2017, its strange motions sparked debate beyond normal astrophysics. Oumuamua accelerated slightly as it left the solar system, an effect not fully explained by gravity alone. Many astronomers attributed the anomaly to outgassing of volatile material, too faint to be visibly detected. Others, however, suggested something more unconventional. Could Oumuamua have been an artificial construct, a probe or fragment of technology from another civilization? Harvard astronomer Avi Loeb became the most prominent voice arguing that possibility, pointing out that a thin, light sail-like object could explain both the acceleration and the absence of a detectable cometary tail. When 3I/ATLAS appeared in 2020, the memory of that debate was fresh. Its breakup seemed more consistent with natural cometary behaviour, yet it left a lingering question. If we had already encountered one possible artificial object, could others follow? Some noted that Oumuamua, Borisov, and Atlas arrived in quick succession, 3 interstellar visitors in only 3 years after centuries of none. Improved detection technology accounted for part of this, but not all. Could the solar system be experiencing a wave of inbound bodies for reasons not yet understood? And could at least one of them have been deliberately sent? The artificial origin hypothesis rests on several lines of reasoning. First is the question of probability. The galaxy contains hundreds of billions of stars, and planetary systems eject vast numbers of comets and asteroids into interstellar space. The odds that some will cross our path are high, but the odds that the first one we detect shows anomalous behaviour is more surprising. Loeb and others argued that we should consider technological explanations, even if unlikely, because ignoring them risks missing evidence. Second is geometry. Oumuamua's trajectory brought it within a comfortable observational distance of Earth, allowing us to study it for weeks. Atlas, too, passed within reach of our telescopes before disintegrating. Statistically, most interstellar bodies should pass unnoticed, too faint or too distant to detect. Yet we observed them at favourable geometries, almost as though placed. Critics dismiss this as selection bias. We naturally detect only those that happen to come close, but the clustering of events still fuels speculation. Third is the issue of lightness. If Oumuamua were thin, With a high area-to-mass ratio, it could respond to solar radiation pressure like a sail. No natural process we know produces kilometre-scale sheets of material with such properties. If artificial, it could be a derelict solar sail or fragment of larger technology. Atlas did not display the same characteristics, but its rapid breakup suggested fragility, perhaps akin to engineered material rather than consolidated rock or ice. This is conjecture, but within scientific speculation, such possibilities are at least considered. Not all experts agree. Most astrophysicists emphasize natural explanations. Tiny jets of sublimating gas can create accelerations too faint to detect directly yet strong enough to alter trajectories. Laboratory experiments with cometry analogues suggest such effects are plausible. They argue that invoking alien technology is unnecessary when standard physics suffices. The debate illustrates a divide in scientific culture. One side favours conservative explanations until forced otherwise, the other encourages broader hypotheses to avoid dismissing rare evidence. For 3I/ATLAS, the artificial debate was more muted. Its disintegration aligned with fragile cometry composition, but questions lingered about its origin. If it came from a distant planetary system, could it have carried more than dust and ice? Some speculated about the possibility of embedded organic molecules or even technosignatures, radio emissions, anomalous reflections, or structured debris. No such evidence was detected, yet the very act of asking these questions shows how the appearance of interstellar visitors shifted the boundary of acceptable speculation. Artificial hypotheses also touch on the issue of intent. If an object like Atlas were artificial, was it functioning or derelict? Could it be a fragment of a probe long since abandoned, drifting through the galaxy for millions of years? Could it be a manufactured messenger, launched to spread information, or simply to exist as evidence of another civilization's reach? Or was it simply debris, the cosmic equivalent of space junk, ejected from a distant system as humans now eject defunct satellites into Earth's orbital graveyard? The scale of interstellar distances complicates these ideas. Even travelling at tens of kilometres per second, an object requires hundreds of thousands of years to cross from one star to the next. Any artificial interstellar probe would be ancient by the time it arrived. Its builders might no longer exist, or might have no knowledge of where it eventually drifted, but that in itself is not disqualifying. Technology outlasting its creators is a plausible outcome of long-lived civilizations. Humanity itself has already launched probes, Voyager, Pioneer, New Horizons, that will wander the galaxy for billions of years. To a distant observer, they may appear as interstellar debris, their artificial nature difficult to confirm without close inspection. 3I/ATLAS reminded us of this parallel. Its breakup into fragments mirrors how human probes, when long abandoned, might one day decay. Solar radiation, micrometeoroid impacts, and internal stresses could shatter structures, leaving only traces. To an alien astronomer observing from afar, the difference between a crumbling comet and a derelict probe might be indistinguishable. Unless one examines the material up close, the line between natural and artificial can blur. This leads to an uncomfortable recognition. Our telescopes, powerful as they are, provide only limited glimpses. Spectra, light curves, and orbital data can tell us much, but not everything. Distinguishing natural from artificial requires proximity missions, and those demand early detection and rapid response. We missed that chance with Atlas. By the time its trajectory was confirmed and the debate arose, the object was already breaking apart and dispersing. If we want answers in the future, we must prepare in advance. Artificial debates, however, are not mere curiosities. They push science forward. By asking whether an object could be engineered, we sharpen the tools needed to test the hypothesis. The search for technosignatures, radio emissions, unnatural spectral lines, structured shapes, becomes more rigorous. Even when the result is natural, the process improves our ability to detect the extraordinary. In this sense, Oumuamua and ATLAS both expanded the frontier of inquiry. Still, the speculation lingers. If Oumuamua was artificial, could a TLAS have been a companion? If Atlas was natural, does that diminish or reinforce the artificial hypothesis for Oumuamua? Each object adds data, but also complexity. 3 visitors in 3 years could be coincidence, or they could represent the first hints of a larger pattern. Until we gather direct evidence, the debate will remain unresolved. suspended between skepticism and wonder. And so the artificial question leads naturally to another. If these objects are natural, why are we seeing them now? Why this sudden clustering, and what does it tell us about the galaxy's flow of interstellar debris?